Okay, it looks like we are now live. I'm starting a little bit earlier just because I've been having some problems with the streaming software when I try to start the stream. Sometimes it's been saying failed to start, so I think there's still some technical issues I'm working out. So what I'm going to do is just get the stream and put it to some of the other places that I have it right now. So let me just put it to Twitter. I'm just going to copy this over. 1 second. Let me just copy this. Oh. 1 second, I'm just trying to. All right. So I don't know how many people are going to be here watching this. Let's see what we've got. Yeah, so let's just sort of recap basically what I did yesterday. So yesterday was the first day of the project. The reason for doing this is that I've always had an interest in quantum mechanics. I've always had an interest in understanding how the world works. That sort of interest came from reading books on physics and those kind of things when I was younger. And the problem is that quantum mechanics is essentially a language in mathematics. If you don't understand complex numbers, superposition, these sort of mathematical concepts that underpin it, a lot of the implications of quantum mechanics are confusing. They don't fit with our regular analogies because the real world isn't really like quantum mechanics at the everyday level. And so this has been sort of my motivation, is that I wanted to learn some of the math. The other motivation was that I have done projects before, most notably the MIT challenge, but also the Year Without English and other projects. And one of the things that I always struggled with when doing those projects was documenting the project, that to actually say what I did, exactly how I did it, and to provide kind of evidence that I did what I said that I did. It was always challenging because I would be studying or working really hard on the project all day. And at the end of the day, you have to go and you have to upload things, you have to write things, you have to really try to document what you did, because it's also easy for you to forget exactly how you did it. And this was particularly true of the Year Without English, where my friend and I, we were doing these kind of mini documentary videos. So we were doing lots of, okay, sit up and do some recording, and we've got to do that now. And so these little snippets that were inserted made things difficult and made it harder to actually do the project. Now, when I was doing those projects, live streaming as it is now didn't really exist. And so I wanted to see whether I could do a project like this live streaming, and the place to start seemed to be with what I knew fairly well right now, which was taking MIT's open classes from MIT OpenCourseWare. So this was sort of a confluence of both a personal interest in learning quantum mechanics, a recognition that just following it wouldn't be enough. I'd actually have to dig into the math, do the practice problems, the real meat of the work, the way that I did with the MIT challenge. And then also wanting to try out a project, an ultra learning project like this, live on camera. So I did the first session yesterday. I've been doing 3 hours in the morning and 3 hours in the afternoon. So 8 a.m. to 11 a.m. Pacific time in the morning, and then 2 p.m. till 5 p.m. in the afternoon. So this is a much lighter schedule than I did during the MIT challenge, but I have to juggle a lot of other work stuff as well. And I think that it will probably be enough. This is not intended to replicate the pace of the MIT challenge. I got done the first 3 lectures in day 1, in addition to looking at the problem sets, whereas typically my goal was to get done about 10 classes per day when I was doing the MIT challenge. So I'm going at a little bit more leisurely pace. But I also wanted to try to take that opportunity to go a little slower, explain why I'm doing certain things, and then also to learn it really deeply, because the goal here is not to pass a certain amount of classes in a certain period of time where I have to keep up a very impressive schedule. There's a lot of quantum mechanics classes. Rather, my goal was to just really get that intuition, that deep insight. So my goals have shifted a little bit as well. So let's just talk a little bit about what I covered yesterday. And those live streams are available on the YouTube channel. So if you have any interest in just kind of either watching the whole thing, if you got lots of time, or if you want to just like kind of hop in and see what I'm doing at various points, you can just click around. But what I did is I started by going over the problem sets. Now, the reason for doing the problem sets and going over the problem sets before actually doing any of the class material, which is not entirely true in my case, because I did about a year ago watch some of these lectures. So there's some residue of that in my mind, but I didn't do any practice. I didn't do any of the math. I just watched some of the lectures just because I was interested, and I was interested in the subject. And part of the reason for doing this project was recognizing that that wasn't going to work for this class at all. But I did the covering of the problem sets first, because I feel like often when you are learning things, you are missing what is the context in which I need to know this information. How is it that I need to know this information? So one of the big things for the MIT challenge is, if you would just watch the lectures, you might convince yourself, oh, I understand this. And then when you move to the problem sets, you'd be like, oh no, I don't understand this at all. And so the reason why is because you have some kind of vague understanding, but you're not quite sure how deep it goes. You can't actually self-check that very easily. This is something called in psychology the illusion of explanatory depth. And so the challenge here, of course, is that when you are doing a class, it's very easy to convince yourself you understand things you don't really understand. And so I like to reverse that, and I like to do the problem sets, or look at the problem sets first, because it gives me that feeling of, oh, I don't know how to solve this. I don't know what the answer is for this. And I didn't spend a lot of time on it, but it gives me a good sense of what do I need to pay attention to and how do I need to pay attention to it. And I think in mathematical classes, again, it's very easy to skip over the derivation, skip over the proofing of the formulas, because, oh, well, that's just math, that's just algebra, it's the concepts that matter. But the problem is that when you get to actually doing the problems and you need to prove certain things, that's the thing that you really need. So we started by going over problem sets 1 to 4. 4 was already getting a point where there were so many concepts that I hadn't covered yet in the class that it was a little difficult to self-gauge. So I decided, okay, I'm not really understanding these problem sets anymore. I'm going to take a pause, I'm going to switch back to doing the lectures. So we did those first 4 problem sets. And then I watched lectures 1 to 3. Did them about 1.5 times the speed for the most part. It was pretty good. As I said, I had watched some of these before. It was a while ago, so I can't give this the fair picture that, you know, this is just, I have never seen any of these materials before. But this time, of course, I'm paying attention to it in a new way, because I know that I'm actually going to be doing these math problems very soon. So started doing that. I just have here my end of day summary. So I like to do a little end of day summary, just sort of what did I learn at the end of the day. Particularly, I did this a lot in the MIT challenge, where I would figure out about what I did, what did I learn, and then I'd also plan for the future because I had limited time and I had to be strategic about, okay, this is where I'm going to go next. This is what I'm going to tackle. So I didn't do the where I'm going to go next because I knew that for today I'm just going to be watching lectures, but we covered 3 classes. The first was just sort of an intro explaining why quantum mechanics is so unintuitive, so weird, so against what you would think the world works like based on your interaction with normal objects. And in that in particular, the prof, Alan Adams, introduced this sort of hypothetical device to try to abstract out some of the more weird physical properties of quantum mechanics, namely hardness and color. And he talked about how if you have a hardness box, you can send in electrons and they'll either come out soft or hard. Obviously, hardness is not a real property. This is just, something that he's using for analogy so you don't get caught up on other physical intuitions. And it'll either come out soft or hard. If you put it into a color box, it'll either come out black or white. And we know that there's 50-50 probability. There's no way of knowing which way the electron's going to come out if you get them from a random source. Okay, so if you take them from a hard box and put them into another hard box and you send them through and you get all the hard electrons and you put them through another hardness box, 100% of them will come out hard. This is how we know that hardness is a certain, in some sense, a property of the electrons. It's not something that's just every time it's random. Same thing with color. If it goes through white, it will come through white. Now, the interesting thing about quantum mechanics is that if you intersect or you interject a color box in between 2 hardness boxes, it resets, and I'm using air quotes here because that's not really what it's doing, but it's kind of resetting the electron so that if it came out hard and then it goes through the color so you know that it's white, it's not that you now know that it's white and hard. If it goes through a second hardness box, it's back to the 50-50 probability again of being either hard or soft. So that's the first little weirdness. Second weirdness is that if you take an apparatus and you have a color box and then a hardness box, and you take both the streams that come out of the hardness box. So let's say you take all the white electrons from a color box, hardness box, both streams, hard and soft, and you use this sort of a device involving mirrors to put the beams back together and then put another color box, which aside from the mirrors, which we know don't interact with the, they don't change the identity of the photons in any way. They're not doing anything funny, or the electrons in any way. Then when we get the electrons coming out the final hardness box, it's as if they didn't go through this hardness box. So the fact that they went through and they were split up and then they were merged again, we had learned from previously that the hardness box resets the electrons. It's not doing that. Once you put the beams back together, it's 100% white, which even if the mirrors and the beams are so distant and so physically separate that you would think that there's no way that they have, the electron either goes one path or the other path, it has no way of knowing which path it went on. So this is, again, very confusing, very unexpected. Then we moved to lecture 2, where we talked about just some basic facts about physics that a quantum theory would have to deal with. So one, it's that atoms exist. So ideally, this quantum mechanical theory should try to explain why atoms exist. 2, that there's randomness, which we already talked about, this 50-50, so it's not purely deterministic. There's atomic spectra, so that if you excite a hydrogen atom and it goes back down, it will release light. So if you, shine some, put some laser or whatever on some hydrogen atoms, you excite them and they go down, they will emit light. But the light they emit, if you put it through a prism, has very, very distinct lines, so that it's not that any type of energy can be emitted from the hydrogen atom. There's very distinct bands, and it forms a very particular mathematical relationship. So this is something to explain, because obviously light in general sources can be any wavelength. So it's not clear why it has to be these exact atomic spectra. Next, we talked about the photoelectric effect, which is actually this explanation of the photoelectric effect is how Einstein won his Nobel Prize. Wasn't for general relativity, wasn't for special relativity, wasn't for his work on a lot of things with quantum mechanics. It was photoelectric effect. Now, the photoelectric effect is that if you shine a light on some metal, depending on the light, it will shoot off electrons. And this was again, photoelectric. So this is the effect that was being measured. And you can get a little apparatus, and it was really actually ingenious that you basically run a voltage through it. So my metaphor is whenever I think of voltage, I try to turn it into height, because voltage is sort of analogous to height. If electricity is to gravity, then voltage is to height. So I try to avoid thinking of voltage as some abstract thing. I try to think of it as trying to move something up in a gravitational field. It's the same sort of idea. So you have a certain voltage, and you can measure the kinetic energy of these electrons that are coming off from the light. And a surprising thing about this is that you would expect that you make a brighter light, you're going to get more energetic photons. Doesn't make a difference. Turns out what makes a difference is the frequency of the light. So higher frequency light, blue light, or X-rays and those kind of things, they shoot the electrons off with a higher velocity. A lower intensity light, red light, microwave light, this kind of thing, it will either shoot the electrons off at a much slower speed, or if it's below a certain threshold, it will not shoot them off at all. And it doesn't matter how much light you shine, it will not shoot off electrons. Now, there's a little bit of complications with that, but this is a general sort of principle. So this was the experiment that showed that light comes in discrete packets or photons, as opposed to just being a continuous medium. Next, we talked about diffraction. So diffraction is the classic double slit experiment. You know what, I'll just go, I even drew some pictures for this. In lecture 2. So if we look at diffraction here, it is a property of waves, any waves, water waves, anything. If you have, let's say, some slits in a paper, and you have waves that are traveling in kind of, plane waves, so meaning they're just sort of lines of troughs, they will sort of radiate in little like circles as they go through the slits. And when they go through the slits, what happens is they start to overlap each other. So the outward sort of waves overlap each other. And then you have this interference pattern, which you can see right here, which is that if you have two crests of the waves, kind of they overlap, you get a super crest. If you get two troughs, you get a super trough. If you get a crest and a trough, they flatten out, right? So this is what's happening with the waves. Now, this is not like particles. If you were to shoot bullets or baseballs through slits, you just see two clumps. They wouldn't be exactly accurate because sometimes they get deflected, or they're, air pressure and whatnot. But you're not going to see interference. The bullets don't, interfere with each other the way waves do. And we know that light is a wave because of diffraction patterns. But now we also know that light is a particle because of photons. And it turns out that if you look at any matter, it has this same effect. So he was saying they've even done this with buckyballs. Now, buckyballs are carbon, I think there's 60 carbon atoms that are arranged like a soccer ball. Now, every carbon atom has numerous particles in it. So this is like thousands of particles. So this is, in human terms, a very small object, but in terms of our understanding of physics, this is a very, very large object in terms of a subatomic scale. And so even this will have this kind of diffraction pattern. So the idea that we know that matter is kind of both wave-like because of this, particle-like because we only ever see it in one place. When you shoot, an electron gun, it makes a little ping at the screen. It's not like distributed over space. It's not a wave like that. So this electron diffraction was, again, one of the facts of life that we had to explain. And then finally, there was this really interesting result called Bell's inequality. And Bell's inequality was essentially, if you look at here, this is the little diagram. Imagine you have three different groups. So you have three different properties. So he talked about in the class, are you an undergrad or not? So it's you either are or you aren't. Are you blonde or not? Are you from Massachusetts or are you not? And the idea here, and this is a little complicated, but the number of people who are both undergrads and not blonde, plus the people who are blonde and not Massachusetts. So I kind of color coded it this way. So you can see this is the penciled area here. This is the dark, like sort of pen area. Must be greater than or equal to the people who are undergrads and not from Massachusetts. That's the highlighted area here. Now, it's a little hard to see from this math that this is true, but if you look visually, you can see that the highlighted area is clearly contained within the other areas. So this is something that we intuitively expect from things. And if you even work out the math, it seems to be just a tautology that this is the case, that the number of these people plus these people must be greater than 0, because if you separate out the components and you subtract, this just logically holds. It doesn't depend on how I draw the circles. Funny thing is, this doesn't apply to quantum mechanics, that you can get situations where, and this is in the case of angular momentum, which we've learned is now the real name of the hardness and soft, that you can get these three different properties that are independent in this way. But if you make this thing, you can make situations where this is smaller than that. And that shows that this sort of naive way of using logic to figure out how these probabilities are adding up doesn't work. And so there's something different going on in quantum mechanics, that this thing which just seemed like a tautology that, well, we're just doing math. There's no experiment here. This is just math, and it's turning out this way. This is showing us that that's the wrong way to do that math, that it is actually the case that you can have these things. So then we moved on to lecture 3, where we talked about waves. And in particular, we had 3 postulates. So the first was that we can represent the sort of state of a particle by this psi wave function. And this is a complex valued wave function. So complex numbers, if you don't remember them, are basically 2-dimensional numbers. So they have a real part and they have an imaginary part, which is at a perpendicular axis to the real ones. They're like this. And so this is just a real function because you can only have one value here. I can't draw it in 3 dimensions on the paper. But complex valued function has both of these. It has a real part and a complex part, and an imaginary part. And the idea is that you can have any wave function specified by this kind of thing. This is the wave function of a particle. And then 2, the meaning of the wave function. What the wave function means is that if you take the norm squared, which is the wave function multiplied by its complex conjugate, if you multiply that together, you get the probability density. So you get the what is the chance of finding it between an interval is the integral defined over that interval. So it's a continuous space, but at the same time, the actual chance of finding something is defined over that interval. So this is what the wave function means, is that it's a probabilistic function of figuring out whether you'll find it at that location. And then the third idea is what's called superposition, which is basically that if you get any 2 wave functions, you can kind of add them together with complex coefficients, and that will also be a wave function. So this was considered to be extremely important. Again, it just seems kind of obvious to me right now, but I think that's probably misleading. He was like, underline this double. This is the most important thing in quantum mechanics, is where you get all the crazy stuff, is that this superposition can happen. So this right here, one of the first results of this is basically the uncertainty relation pops out of this wave int function, because waves, if you can think of a wave as having high momentum, meaning that it is very high frequency, which is what we know from light, very high frequency, then it means that it's necessarily very sharply peaked. Like, so if this was in the, if it has a very defined, if it has a very defined, rather, not very high, there's a very defined frequency, then if you do the Fourier transform of that, which is to turn the frequency, the inverse Fourier transform is to turn frequency into position, Fourier transform is to turn position into frequency. But you do the Fourier transform, basically they flip each other around. So something that is a pure sine wave is just one point in the Fourier transform, whereas a single point is a sine wave in the Fourier transform. And because of this relationship, something that you know exactly where it is, meaning it's one point, it exists only in one space, is actually super spread out in terms of its momentum, meaning that you have really no idea how fast this thing is moving. Whereas something that is super spread out, meaning that it's a pure sine wave, it just extends all over, is something that you have a very good idea of where it is, how fast it is moving, but you have no idea of where it is. So this is an uncertainty relation. It just pops out of the fact that we're dealing with waves. So this is, again, something that I'm getting at here for these classes, is that I'm trying to understand these sort of results. And there's a lot of math here. I haven't been going through it again super fast yet. I only did the first 3 lectures. My goal now is to shift over to doing more of the lectures. I want to try to get it done, maybe, we'll see how much time we have, but I would like to try to get done about 5 today. It depends. If it's taking a lot of math, it might take a little longer. I'm going to try to just work through lectures. So I'll just take little pauses after the lectures, do an active recall, explain what I've learned, try to get it out there. And then If we can finish the 5 lectures today, my goal is to get to lecture 10, cover the first 10 lectures. There's 24 in the class. If I can get done the first 10 lectures, that covers up to problem sets 5. Then I'm going to shift gears, work on problem sets for the rest of the week. And then starting on Monday, regardless of how far I get in the problem sets, I'm going to start going back to classes, finish the rest of the classes, and then I'm going to spend the rest of the process doing problem sets, fixing weaknesses in my mathematics. I wanted to cover all the classes by about April 15th because I feel like I want to have a good 2 weeks to decide, okay, I need to work on this, I need to work on that. And I think that my problems are going to be mathematical just because I have all the stuff for math I've covered. I covered about 8 years ago in the MIT challenge. And there's even a class that I didn't cover, 803 waves. So there might be stuff pertaining to waves that I don't know. And so I might have to go back and relearn it. I might have to brush up on some of my more basic calculus, linear algebra, you know, all these various things that are kind of hazy and a little bit half remembered. So I want to get through the lectures first so that I can identify weaknesses, repair them, and then hopefully near the end of the class, I can work on a final exam. And, you know, if this goes super well and I'm going super well, I might even touch a little bit of the next class because this is just the first in a series of quantum mechanics. But my goal is to just cover this class in as much depth as possible. So if it doesn't look like I've got a ton of time, I'll just go a little deeper with that. So I am going to start lecture number 4 now. So let me just write here. And I've said this before, but I'll say it again. When you're watching the lectures, you're watching me watching a video. And I know that's not the most compelling content, but I want to kind of show you how I'm doing things. But because of this, it's going to maybe have a little bit of choppiness. There's not really much I can do. It's just sort of the live stream. However, if you are following along and you do really want to hear what he's saying in the lecture, you don't want to just watch me, then my advice is to go to the website. So if you just Google MIT OpenCourseWare, and then this is the spring 2013 session. You can just follow whatever lecture we're watching, and you could just, you know, either put me on mute and do this, or you could put your video on mute and watch it at the same time and just try to match up. Again, my point is mostly to show how I go through a class rather than to necessarily make it super easy for you to follow along. So I'm going to be going at 1.5 times the speed probably for some of it. I might go slower if they're doing math or doing things that I need to jot it down and I don't have enough time, or if I don't understand what they're being said. So let's jump over to doing one of these right now.
The following content is for.
So let me just reload this. All right. So I'm going to try to scale this roughly so that I can still see the chat, but I won't have to see my my own video because I find it very distracting to watch 2 versions of the same class on the same window. So you'll have to bear with me as I figure out this live streaming thing. All right, let's go.
Provided under a Creative Commons license. Your OpenCourseWare continue to offer high-quality education free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
Anything lingering and disturbing or bewildering? No? Nothing? All right. Okay, so the story so far, or you get coffee. The story so far is basically 3 postulates. The first of a particle, is given by or described by a wave function psi x. Yeah. So in particular, just to flesh this out a little more, if we were in 3D, for example, which we're not, we're currently in our one-dimensional cryptographic circle, in 3D, the wave function would be a function of all 3 positions, x, y, and z. If we had 2 particles, our wave function would be a function of the position of each particle. X1, x2, and so on. So we'll go through lots of details and examples later on, but for the most part, we're going to be sticking with single particle in 1 dimension for the next few weeks. And again, I want to emphasize that this is our first pass through our definition of quantum mechanics. Once we've used the language and the theory a little bit, we're going to develop a more general, more coherent set of rules for definition of quantum mechanics. But this is our first pass. 2. The meaning of the wave function is that the norm squared, psi of x, norm squared, it's complex, dx is the probability of finding the particle. What's this in there? Finding the particle in the region between x and x plus dx. So So psi squared itself, norm squared, is the probability density. Okay. And third, the superposition principle. If there are two possible configurations the system can be in, which in quantum mechanics means two different wave functions that could describe the system, given psi 1 and psi 2, two wave functions that could describe two different configurations of the system, for example, particles here or the particles over here. It's also possible to find the system in a superposition of those two. Psi is equal to some arbitrary linear combination alpha psi 1 plus beta psi 2 of x. Okay? So some things to know. Two questions about this before we move on. Questions? Nothing? Really? You're maybe threatening me with something. I know there are questions. This is not trivial stuff. Okay. So some things to know. The first is we want to normalize. We will generally normalize and require that the integral over all possible positions of the probability density, psi of x, norm squared, is equal to 1. This is just saying that the total probability that we find a particle somewhere had better be 1. This is like saying if I know a particle is in one of two boxes, because I put a particle in one of the boxes, I just don't remember which one, then the probability that's in the first box plus the probability in the second box, 1. If it's less, then the particle simply disappears. And basic rule, things don't just disappear. So probability should be normalized. This is a prescription. So a second thing to note is that all reasonable or non-stupid functions, psi of x, are equally reasonable as wave functions. Okay, so this is a very reasonable function. It's nice and smooth. It converges to 0 at infinity. It's, it's got all the nice properties you might want. This is also a reasonable function. It's a little annoying, but there it is. And they're both perfectly reasonable as wave functions. This, on the other hand, not so much. So for two reasons. First off, it's discontinuous, and as you're going to show in your problem set, discontinuities are very bad for wave functions, so we need our wave function to be continuous. The second is, over some domain, it's multi-valued, but two different values of the function. That's also bad because what's the probability? It's the norm squared, which has two values. Two values for the probability. That doesn't make any sense. What's the probability that I'm going to fall over in 10 seconds? Well, it's actually equals 1% or 3%. It's one of those, right? So it's always much lower than that. So all reasonable wave functions are probably reasonable functions are equally reasonable as wave functions. And in particular, what that means is all states corresponding to reasonable wave functions are equally reasonable as physical states. There's no primacy in wave functions or in states. However, with that said, some wave functions are more equal than others. Okay? And this is important, and playing with the definition, this is going to be we're challenged for the next couple of lectures. So in particular, this wave function has a nice simple application. If I'm saying this is psi of x, then what can you tell me about the particle whose wave function is this psi of x? What do you have about? Where do you know? It's here, right? It's not over here. Probability is basically 0. Probability is large. It's pretty much here. It's very common. What about this guy? Less informative, right? It's less obvious what this wave function is telling you. So some wave functions are more equal in the sense that they have, i.e., they have symbol interpretations. So for example, this wave function, continuing on, this wave function doesn't tell me where the particle is. What does it tell me? Exactly. So this is giving me information about the particle is on wavelength. So this one, I would also say is more equal than this one. They're both perfectly physical, but this one has a simple interpretation, and that's going to be important for us. Okay. Related to that is that any reasonable function, subject, can be expressed as the superposition of more equal wave functions.
I apologize in advance. It looks like some people outside are doing some yard work, and it might make some noise that will interrupt the stream, but nonetheless, we'll soldier on.
We saw this last time in the Fourier theorem. Fourier theorem said, look, take any wave function, take an interpret like quantum mechanics, take any wave function which is given by some complex value function, and it can be expressed as a superposition of plane waves. Integral over 2pi, normalization, integral dk, sine tilde of k, this is a set of coefficients, easy kx. So what are we doing here? We're saying, take a value of k. There's a number associated with it. There's going to be an amplitude of phase, a magnitude of phase. And that's the magnitude phase of a plane wave, e to the I kx. And remember that e to the I kx is equal to cos kx plus sine kx. You should know, but just to remind you, this is a periodic function. These are periodic functions. So this is a plane wave with a definite wavelength, 2pi upon k. So this is a more equal wave function in the sense that it has a definite wavelength. We know what its momentum is. Momentum is h bar k. Any function, we're saying, can be expressed as a superposition of summing over all possible values of k, all possible different wavelengths. Any function can be expressed as a superposition of wave functions with a definite momentum. That makes sense? Free to think about it that way. But for the quantum mechanics, this is the way we want to think about it. It's just a true statement. It's a mathematical fact. Questions about that? Similarly, I claim that I can expand the very same function, psi of x, as a superposition of states not with definite momentum, but of states with definite position. So what's a state with a definite position? Yeah, a delta function, exactly. So I claim that any function, psi of x, can be expanded, a sum, over all states with a definite position, so delta of, well, what's the state with a definite position? X naught. Delta of x minus x naught. Okay, this goes being when x naught is equal to x. Okay, but I want to sum over all possible delta functions, that means all possible positions, that means all possible values of x naught, dx naught. And it needs a coefficient function here. Well, the coefficient function I'm going to call psi of x naught. So is this true? Is it true that I can take any function and expand it into the superposition of delta functions? Absolutely, because look what this equation does. This integral, remember, delta function is your friend. It's a map from integrals to numbers or functions. So this integral is an integral over x naught. Here we have the delta of x minus x naught. This basically says the value of this integral is what you get by taking the integrand and replacing x by x naught. Set x equal to x naught, that's when delta is 0. So this is equal to the argument evaluated x naught is equal to x. That's just psi of x. Okay. Any arbitrarily ugly function can be expressed either as a superposition of states with definite momentum or a superposition of states with definite position. Okay. And this is going to be true. We're going to find that this is a general statement that any state can be expressed as a superposition of states with a well-defined observable quantity for any observable quantity we want. So let me give you just a quick little bit of intuition. In 2D, this is a perfectly good vector, right? And here's the question I want to ask you. Is that a superposition? Yeah, I mean, every vector can be written as the sum of other vectors, right? And it can be done in an infinite number of ways, right? So there's no such thing as a state which is not a superposition. Every vector is a superposition of other vectors. It's a sum of other vectors. So, in particular, we often find it useful to pick a basis and say, look, I know what I mean by the vector y. Y has to be a vector in this direction. I know what I mean by vector x hat direction. And now I can ask, given that these are my natural guys, the guys that I want to attend to, is this a superposition of x and y, or is it just x or y? Well, that's a superposition, whereas x hat itself is not. So somehow this is about finding a convenient choice of basis. But any given vector can be expressed as a superposition of some pair of basis vectors, or a different pair of basis vectors, right? There's nothing hallowed about your choice of basis. There's no God-given basis for the universe. You look at the universe, the Hubble field, and you don't see somewhere in the Hubble field an arrow going x, right? So there's no natural choice of basis, but it's sometimes convenient to pick a basis. This is the direction of the surface of the Earth. This is the direction perpendicular to it, right? So sometimes particular basis sets have particular meanings to us. That's true in vectors. This is along the Earth. This is perpendicular to it. This would be slightly strange. It would be your meaning. And similarly, this is an expansion of a function as a sum, as a superposition of other functions. And you could have done this in any good space of functions. We'll talk about that more. These are equally natural ones. They're more equal. These are ones with different definite values of position, different definite values of momentum. Very cool? Quickly, what's the momentum associated with the plane of EBIKX? H bar K. Okay. So, good. So now I want to just quickly run over some concept questions for you. So, what about your clickers? Okay, well, we'll do this verbally.
How would you physically interpret the wave function in the sketch? It's a large particle, it's a small particle. It's a particle located at a definite spot, x0. I would guess either E, or if we're considering the fact that there's discontinuities, so it's either E or A, just because because it looks like there's sharp corners here. But if this is just sort of meant to be a kind of a sketch and we're supposed to ignore those sharp corners, then I would say it's E.
Okay. Oops. Oh. All right, let's do this again. So, how would you interpret this wave function? E. Solid. Yeah. All right. How do you know whether the particle is big or small by looking at the wave function? Okay. All right. Two particles.
Two particles, 1 and 2, are described by a plane wave of the form exponential e to the ikx. Particle 1 has a smaller wavelength than particle 2. Which particle has the larger momentum? Well, the particle that has the shorter wavelength has the larger momentum, so that would be particle 1.
Described by a plane wave of the form EBIKX. Particle 1 is a smaller wavelength than particle 2. Which particle has a larger momentum? Think about it, don't say it. Okay, and this sort of defeats the purpose of the clicker thing, because now I'm supposed to be able to know without you guys saying anything. So instead of saying that loud, here's what I'd like you to do. Talk to the person next to you and discuss which one has the larger momentum.
If you want to learn how to learn math, I do have an article. Just Google Scott H. Young, how to learn math.
How come? Right, smaller wavelength. P equals H bar K. K equals 2 pi over lambda. Solid? Okay. Smaller wavelength, higher momentum. If it has higher momentum, what do you expect to know about its energy? It's probably higher. Are you positive about that? No, you need to know how the energy depends on the momentum, but it's probably higher. So this is an important little lesson that you probably will know from optics and from quantum mechanics. Shorter wavelength things, higher energy. Higher momentum for sure, usually higher energy as well. Very useful rule of thumb to keep in mind. Okay, indeed, it's particle 1. Okay, next one. Compared to the wave function psi of x, its Fourier transform, psi tilde of x, contains more information or less, or the same, or something about it. Don't say it out loud, just...
Same information.
Okay. So how many people know the answer? Awesome. How many people are not sure? Okay, so there's a good. So talk to the person next to you and convince them. Briefly. All right. Good. So let's vote. A, more information. B, less information. C, the same. Yeah, okay, good. You got it. Yeah. All right. So these are not hard ones. Okay. This function, which is a sine wave of length L.
Consider a function fx, which is a sine wave of length L. F of x equals sine kx between this section, or it equals 0 elsewhere. Which statement is closer to the truth? A has a single well-defined wavelength. B is made up of a range of wavelengths. So it's going to be B because only if it extended out forever, it would, but it requires contributions of other wavelengths in order to suppress the sine wave outside of that range.
0 outside of that region. Which is closer to true? F has a single well-defined wavelength for the most part. It's closer to true because it doesn't have to be exact. F has a single well-defined wavelength, or F is made up of a wide range of wavelengths. Okay, think it to yourself. Ponder that one for a minute. Okay, now before we get talking about it, hold on. I want everyone, since we don't have clickers, but I want to pull off the same effect, and we can do this because it's binary here. I want everyone close your eyes. Just close your eyes, just for a moment. Yeah, or close the person next to you. That's fine. And now I want you to vote. Okay, A is F has a single well-defined wavelength. B is F has a wide range of wavelengths. So how many people think A, a single wavelength? Okay, lower your hands. Good. And how many people think B, a wide range of wavelengths? Awesome. So this is exactly what happens when we actually use clickers. It's 50-50. So now you guys need to talk to the person next to you and convince each other of the truth. All right. So the volume sort of tones down as people, I think, come to resolution. Close your eyes again. Once more is the preach, my friends. So close your eyes, and now let's vote again. F of x has a single well-defined wavelength. And now F of x is made up of a range of wavelengths. Okay, there's a dramatic shift in the field to B. It has a wide range of wavelengths, not a single wavelength, and that is in fact the correct answer. So yay! Okay, so learning happens. That was an empirical test. So does anyone want to defend this view that F is made up of a wide range of wavelengths? Sure.
So the sine wave is infinite, and it cancels out asymptotes over 2 and positive over 2, which means you need to add a bunch of wavelengths to actually cancel that out there.
Awesome. Exactly. If you only had the thing of single wavelength, it would continue.
This is 804 Quantum Physics 1 by MIT.
What can you say about it? We know that a sine wave is continuous. It's continuous everywhere, right? It's also differentiable everywhere. Its derivative is continuous and differentiable everywhere because it's a cosine, right? So if you take a superposition of sines and cosines, do you ever get a discontinuity? No. Do you ever get something whose derivative is discontinuous? No. So how would you ever reproduce a thing with a discontinuity using sines and cosines? Well, you need some infinite sum of sines and cosines where there's some technicality about the infinite limit being singular. Right? So you can't do it with a finite number of sines and cosines. That function is continuous, but its derivative is discontinuous. Yeah? So it's going to take an infinite number of sines and cosines to reproduce that little key to the edge. Yeah?
The finite number of sines and cosines doesn't mean finite. Or an infinite number of sines and cosines doesn't mean infinite range of sines and cosines, right? Because over time,
that's true. You need arbitrarily. So let's talk about that. That's the next question. So the question is, that's a very good question. The question here is, look, there's two different things you can talk about. One is arbitrarily large and arbitrarily short wavelengths, an arbitrary range of wavelengths, and the other is an infinite number. But an infinite number is silly because there's a continuous variable here, k. You have an infinite number of wavelengths between 1 and 1.2. Right? It's continuous. So which one do you need? So let's go back to this connection that we got a minute ago from short distance and high length. Okay. It looks like I had 1 kilo wavelength, but I think in order to reproduce as a superposition of state with definite method, I need arbitrarily high wavelength. And why do I need arbitrarily high wavelength? Why do I need arbitrarily high length the most? Well, it's because of this. We have cake. And this feature, what's the length scale of that feature? It's infinitesimally small, which means that in order to reproduce that, we need momentum that's arbitrarily large. So it's really about the range, not just the number. Right? So you need arbitrarily large momentum to construct or detect an arbitrarily small feature. You mean our large modes? Yeah. I chose to phrase it that way because I want to emphasize and encourage, that's what you think, and encourage you to conflate short distance and large momentum. I want the connection between momentum and length scale to be something that becomes intuitive to you. So when I talk about something with short features, I'm going to talk about it as something with large momentum. And that's because in a quantum mechanical system, something with short wavelength is something that carries large momentum. Is that cool? Great, good question.
So earlier you said that like any reasonable wave function is like a possible wave function.
Yeah.
Does that mean it has to be Fourier transformable?
Yeah, that's usually a condition. Yeah, exactly. We don't phrase it that way. In fact, there's a problem in your problem set that will walk you through what we will need, what should be true of the Fourier transform in order for this to be a reasonable wave function. And among other things, your intuition here is correct. Among other things, being able to have a Fourier transform where you don't have arbitrarily high momentum modes is going to be an important condition. That's going to turn out to be related to the derivative being continuous. That's a very good question. So that's the optional problem E on problem set 2. Okay. Other questions? All right. Cool. So that's it for the clicker questions. Sorry for the technology fail. Okay. So I'm just going to turn this off and discuss. That's really irritating. So today what I want to do is pick up the discussion of the uncertainty principle that we sort of outlined previously. The fact that when we have a wave function with reasonably well-defined position corresponding to a particle with reasonably well-defined position, it didn't have a reasonably well-defined momentum, and vice versa. The certainty of the momentum seems to imply lack of knowledge about the position, and vice versa. So in order to do that, we need to define probability or define uncertainty. So I need to define things about X and delta T. So first, I just want to run through what should be totally remedial probability, but it's always useful to just remember how these basic things work. So consider a set of people in a room, and I want to plot the number of people with a particular age as a function of the age, possible ages. So let's say we have 16 people, and at 14 we have 1, and at 15 we have 1, and at 16 we have 3, and at 16, and at 20 we have 2, and at 21 we have 4, and at 22 we have 5. And that's it. Okay. So 1, 3, 2, 4, 5. Okay. So what's the probability that any given person in this group of 16 has a particular age? I'll call it A. Okay. So how do we compute the probability that they have age A? Well, this is easy. It's the number that have age A over the total number. Okay. So note an important side note, which is that the sum over all possible ages of the probability that you have age A is equal to 1, because it's just going to be the sum of the number with particular age over the total number, which is just the sum of the number with any given age. So here's some questions. So what's the most likely age? If you grab one of these people from the room with a giant director set, pull out a person and let them dangle and ask them what their age is, what's the most likely age they'll have?
22.
22. On the other hand, what's the average age?
I don't know, 19.
We'll just talk eyeball roughly. What do you think it is? Yeah, it's around 19 or 20. So just be 19.2 for this. Okay. But if everyone has a little sticker on their little pebble that says like 14, 15, 16, 20, 21, or 22, how many people have the age 19.2? None, right? So a useful thing is that the average need not be an observable value. This is going to come back on. So 19.4. That's what I got. So in particular, how did I get the average? So I'm going to define some notation.
Yeah, it's 1.5 times speed. This is how he speaks normally.
How do I compute it? So we all know this, but let me just be explicit about it. It's the sum.
I'm going faster. I'm doing 1.5 because that's about the level I can understand in.
People with that age times the age divided by the total number of people. Okay. So in this case, I go 14, 14, 16, 16, 16, 20, 20, 21, 21, 21, 21, 22, 22, 22, right? And so that's all I've written. Notice I can write this in a nice way. This is equal to the sum over all possible ages of A times the ratio of NA to N total. The ratio of NA to N total, that's just the probability that any given this person has probability A. A times probability of A. So the expected value is the sum over all possible values of the value times the probability you get that value. Yeah? So I'm just this is the same equation, but in a box.
This is just expected value.
Relation. And so again, does the average have to be measurable? No, it certainly doesn't. And it usually isn't. So let's ask the same thing for the square integers. What is the average of A squared? Square the ages. You might say, well, why would I ever care about that? Well, let's just be explicit about it. So following the same logic here, the average of A squared, the average value of the square of the ages is, well, I'm going to do exactly the same thing, it's just A squared, right? 14 squared, 15 squared, 16 squared, 16, 16 squared. So this is going to give me exactly the same expression. So over A of A squared, probability of measuring A. And more generally, the expected value, or the average value of some function of A, is, and this is something you don't usually do, is equal to the sum over A of f of A, the value of f given a particular value of A, times the probability that you measure that value of A in the first place. Okay. It's exactly the same logic as averages. Right, cool. So here's a quick question. Is squared equal to the expected value of A squared?
No.
Right, in general, no, not necessarily. Right. So for example, the average value, suppose we have a Gaussian centered in the origin, so here's A. Now A is an age, but it's something I don't include like infants and whatever inside is, happiness on a given day. So what's the average value? Meh, right? Sort of vaguely neutral, right? On the other hand, if you take A squared, very few people have A squared as 0. Most people have A squared as not a 0 value. And most people are sort of in the middle. Most people are sort of hazy on what the day is. So in this case, it's 0. The expected value of A, or the average value of A is 0. The average value of A squared is not equal to 0. Yeah? And that's because the squared has everything positive. So how do we characterize? This gives us a useful tool for characterizing the width of a distribution. So here we have a distribution where its average value is 0, but its width is not 0. And then the expectation value of A squared, the expected value of A squared is not 0. So how do we define the width of a distribution? It's going to be like uncertainty. How happy are you today? I'm not sure. How unsure are you? Well, that's just a precise measure. So let me define 3 things. First, the deviation. So the deviation is going to be A minus the average value of A. So this is just take the actual value of A and subtract off the average value of A. So we always get something that's centered at 0. Okay. Right, like this. Note, by the way, just a convenient thing to note, the average value of A minus its average value. Well, what's the average value of 7? 7, right? Okay, good. So that first term is the average value of A, the average value of A, and that second term is the average value of this number, which is just this number minus A. So it's 0. Yeah? The average value of a number is 0, the average value of this variable is the average value of that variable, but that's 0. Okay, so deviation is not a terribly good thing on average, because on average the deviation is always 0. That's what it means to say this is the average. So the deviation say how far is any particular instance from that average. If you average those deviations, they always give you 0. So this is not a very good measure of the actual width of the system, but we can get a nice measure by getting the deviation squared. Okay, and let's take the mean of the deviation squared. So the mean of the deviation squared, mean of A minus the average value of A squared. Okay. This is what I'm going to call the standard deviation. Which is a little odd because really you don't call it standard deviation squared, but whatever. We use funny words. And what does it mean if, so now what does it mean if the average value of A is 0? It means it's centered at 0. What does it mean if the standard deviation of A is 0? Yeah, so if the standard deviation is 0, then the distribution has no width, right? Because if there was any amplitude away from the average value, then that would give a non-zero, strictly positive contribution to this average expectation, and this wouldn't be 0 anymore. So standard deviation is 0, so there's no width, which is why standard deviation.
I think it's important to note that my understanding of standard deviation would be the square root of this. This would be the variance, no?
Taking this seriously and taking this square. So standard deviation squared, this is going to be equal to the average value of A squared minus twice A times the average value of A plus average value of A quantity squared. But if you do this out, this is going to be equal to A squared minus 2A average value of A average value of A. That's just minus twice the average value of A quantity squared. And then plus average value of A squared. So this is an alternate way of writing standard deviation. Okay, so we can either write it in this fashion or this fashion. And the notation for this is delta A squared. Okay, so when I talk about an uncertainty, what I mean is, given my distribution, I compute the standard deviation, and the uncertainty is going to be the square root of the standard deviation squared. Okay. So delta A, then the words I can use for this is the uncertainty in A, given some probability distribution. Different probability distributions are going to give me different delta A's. So one thing that's sort of annoying is that when you write delta A, there's nothing in the notation that says which distribution you were talking about. When you have multiple distributions or multiple possible probability distributions, sometimes it's useful to just put even the probability distribution in it. This is not very often used, but sometimes it's very helpful when you're doing calculations, just keep track. Are we cool with that? Yeah, questions? Yeah, delta A squared, yeah. Other questions? Okay, sorry, yeah. Yeah, it's just, this is a notation that's used typically, so I didn't put the parentheses around precisely to alert you to the stupidities of this notation. Okay, so any other questions? Okay, so let's just do the same thing for continuous variables. Now for continuous variables. Okay, I'm just going to write the expressions and just get them out of the way. So the average value of some x given a probability distribution on x, where x is a continuous variable, it can be equal to the integral. Let's just say x is defined from minus infinity to infinity, which is pretty useful, or pretty typical. Minus infinity to infinity, dx, probability distribution of x times x. should use curvy, I should use x. Okay. And similarly, for x squared, or more generally for f of x, the average value of f of x, or the expected value of f of x given this probability distribution, is going to be equal to the integral dx, it's infinity to infinity, the probability distribution of x, of f of x, in direct analogy to what we had before. But, so this is all just mathematics, and we define the uncertainty in x is equal to the expectation value of x squared minus the expected value of x quantity squared. Okay. And this is of x squared. Thanks. If you see me dropping an exponent or a factor of 2, please tell me. So thank you for that. So all of that is just straight up classical probability theory. And now I just want to write this in the notation of quantum mechanics. Given this, that the system is in a state described by the wave function psi of x, the average value, the expected value of x, the typical value if you just observe the particle at some moment, is equal to the integral over all possible values of x.
I'm just going to copy this down into this because I think this is relevant here. This is the dx px f of x squared, not squared there, I'll put sorry, x squared, this is why you don't use pen, minus dx x.
The probability distribution, psi of x, norm squared, x. And similarly, for any function of x, the expected value is going to be equal to dx. The probability distribution is given by the norm squared of the wave function times f of x, minus infinity to infinity. Okay, and same definition for uncertainty. And again, this notation is really dangerous because the expected value of x depends on the probability distribution. In a physical system, the expected value of x depends on what the state of the system is, what the wave function is. And this notation doesn't indicate that. So there are a couple of ways to improve this notation, one of which is, so this is, again, sort of side note, one way to improve this notation x is to write the expected value of x in the state psi, so you write psi as a subscript. Another notation that we'll come back, you'll see why this is a useful notation later in the semester, is this notation, psi. And we will give meaning to this notation later, but I just want to alert you that it's used throughout books, and all it means the same thing as what we're talking about, the expected value of x, given a particular state psi. Okay? Yeah?
Expected value of momentum, you need to transform.
Excellent question. Excellent question. Okay, so the question is, how do we do the same thing for momentum? If you want to compute the expected value of momentum, what do you have to do? You have to do some Fourier transform to the wave function. So this is a question that you're going to answer on the problem set, and we made a guess for last time. But quickly, let's just think about what it's going to be purely formally. Formally, if we want to know the likely value of the momentum, the likely value of the momentum is a continuous variable, just like any other observable variable. We can write as the integral over all possible values of momentum from, let's say, it could be minus infinity to infinity. The probability of having that momentum times momentum. Right? Or well, this is tautology, right? This is what you mean by probability. But we need to know if we have a quantum mechanical system described by a state psi of x, how do we compute the probability of measure p? Do you want to do this one? Yeah, okay. And we made a guess, question mark, we made a guess at the end of the last lecture that in quantum mechanics, this should be dp minus infinity to infinity of the Fourier transform, psi tilde of p, up to an h bar factor, psi tilde of p, the Fourier transform, p, norm squared. Okay, so we're guessing that the Fourier transform norm squared is equal to the probability of measuring the associated momentum. Okay, so that's a guess. That's a guess. And so on your problem, you can prove it. Okay, so exactly the same logic goes through. It's a very good question. Thanks. Other questions? Yeah. So this is the probability of measuring momentum p, and that's the value of p. We're talking about all p's. This is the probability, and that's actually p. Okay, so the Fourier transform is a function of momentum in the same way that the wave function is a function of the position. Right? So this is a function of momentum. It's norm squared. Defines the probability. And then the p on the right is this p, the expected value of p, the average value of p. Does that make sense? Cool. Yeah? No, so that's a very good question. So let's go back to that very good question. So the question, let me phrase it in terms of position, because the same question comes up. Thank you for asking that. Look at this. This is weird. Actually, I'm going to phrase this as a dimensional analysis question. Tell me if this is the same question as you're asking. This is the thing with dimensions of what? Length, right? The overall line is that we have a length and a probability, which is a number, and then another length. That looks like x squared. Right? So why are we getting something in the dimensions of length, not something in the dimensions of length squared? And the answer is this is not a probability, it is a probability density. Okay, so it's got units of probability per unit length. So this has dimensions of 1 over length. So this quantity, p of x dx, tells me the probability, which is a pure number, no dimensions, the probability to find the particle between x and x plus dx. Cool? So that was our first postulate, our second postulate. Psi of x and dx squared is probability of finding it in this domain. And so what we're doing is we're summing over all such domains the probability times the value. Cool? So this is the difference between discrete, where we didn't have these probabilities, where discrete, where we didn't have these probability densities, we just had numbers, two numbers, and two probabilities. Now we have probability densities per unit, whatever. Yeah. How do you pronounce good? That's a good question. The question is, how do we pronounce these things? So this is called the expected value of x, or the average value of x, or most typically in quantum mechanics, the expectation value of x. So you can call it anything you want. This is the same thing. The psi is just to denote that that this is in the state psi. It can be pronounced in two ways. You can say the expectation value of x, or the expectation value of x in the state psi. Okay, and this would be pronounced one of two ways: the expectation value of x in the state psi, or psi x psi. Yeah, that's a very good question. So, but they mean the same thing. Now, I should emphasize that when, you can have two ways of describing something that mean the same thing, but they carry different connotations, right? Like, I don't know, like, I have a friend who's like a really nice guy. He's a mensch, he's a good guy. And so I can say like he's a nice guy, or I can say he's cariñoso. And they mean different things in different languages. It's the same idea, but they have different flavors, right? So, whatever your native language is, you've got some analog of this. This means something in a particular mathematical language we're talking about quantum mechanics. This has a different flavor. It carries different implications. And we'll see what that is later. We haven't got there yet. Yeah. Why is there a double notation of psi? Yeah, we'll see later. Roughly speaking, it's because in computing this expectation value, there's a psi squared. And so this is to remind you of that. Other questions? Terminology is one of the most annoying features of quantum mechanics, yeah?
So things like this, right? So at the beginning when it's doing it,
Yes.
how is that the
That's a very good question. In order to answer that question, we need to actually work out the uncertainty relation. So the question is, look, this is some choice of uncertainty. You could have chosen some other definition of uncertainty. You could have considered, the expectation value of x to the fourth minus x to the fourth, and taken the fourth root of that. So why this one? And one answer is, indeed, the uncertainty relation works out quite nicely. But I think the important thing to say here is that there are many ways you could construct quantities. This is a convenient one, and it's one that has nice properties that we like. There is no God-given reason why this had to be the right thing. Okay. I can say more, but I don't want to take the time to do it. So ask in office hours. Okay, good. But the second part of your question was, why does the Heisenberg relation work out nicely in terms of these guys? And we will study that in extraordinary detail. We will see that. So we're going to drive it twice, soon and then later. The later version is better. So let me work out some examples. Or actually, you know what? I'm going to skip the examples in the interest of time. They're in the notes, and so they'll be posted on the webpage. By the way, the first 18 lectures of notes are posted. I had a busy night last night. So let's come back to computing expectation values for momentum. So I want to go back to this and ask this like before. I want to make some progress towards deriving this relation. So I want to start over on the definition of the expected value of momentum. And I'd like to do it directly in terms of the wave function. So how do we do this? So one way of saying this is, what's the average value of p? Well, I can phrase this in terms of the wave function the following way. I'm going to sum over all positions, dx, expectation value of x squared from minus infinity to infinity. And then the momentum associated to the value of x. Okay, so it's tempting to write something like this down and think that maybe there's some p of x. This is a tempting thing to write down. Can we? Are we ever in a position to say intelligently that a particle, that an electron is both hard and white? No, because being hard is a superposition of being black and white, right? Are we ever in a position to say that our particle has a definite position x and correspondingly a definite momentum p? It's not that we don't get to it, it's that it doesn't make sense to do so. In general, being in a definite position means being in a superposition of having definite momentum for different values of momentum. Yeah? And if you want a sharp way of saying this, look at these relations. I claim that any function can be expressed as a superposition of states with definite momentum, right? Well, among other things, a state with definite position, x naught, can be written as a superposition of root 2 pi. Integral dk. I'll call this delta tilde. Okay. E to the ikx. And if you haven't played with delta functions before and you haven't seen this, then you will on the problem side, because we have a problem that works through great many details. But in particular, it's clear that this quantity can't be a delta function of k, because in order this would be just using the ikx, that's definitely not a delta function. Meanwhile, what can you say about the singularity structure the continuity structure of a delta function? Is it continuous? No. Its derivative isn't continuous. Its second derivative, none of its derivatives are in any way continuous. They're all absolutely horrible. Okay? So how many momentum modes am I going to need to superimpose in order to reproduce a function that has this sort of structure? An infinite number. And it turns out it's going to be an infinite number with the same amplitude, slightly different phase. Okay? So you can never say that you're in a state with definite position and definite momentum. Being in a state with definite position means being in a superposition of being in a superposition. And in fact, I'm just going to write out the answer here. E to the I, k, inside k, x naught. Being in a state with definite position means being in a superposition of states with arbitrary momentum, and vice versa. You cannot be in a state with definite position, definite momentum. So this doesn't work. So what we want is we want some good definition. So this does not work. We want some good definition of P given that we're working with a wave function, which is a function of x. What is that good definition of the momentum? So we have a couple of hints. So hit the first. So this is what we're after. Hint the first is that a wave, we know that given a wave with wave number k, which is equal to 2 pi over lambda, is associated, according to de Broglie and according to the Davis-Grömer experiments, to a plane, to a particle. So having a particle, a wave with wave number k or wavelength lambda is associated with a particle with momentum p is equal to h bar k. Yeah. But in particular, what does a plane with wavelength lambda or wave number k look like? That's e to the ikx. And if I have a wave, a plane wave e to the ikx, how do I get h bar k out of it? Okay. Note the following. The derivative with respect to x, well, actually, let me get this down here.
So I like to slow down when he starts doing math that I don't find super obvious because it's a little hard to keep up with his writing at 1.9 times speed.
Is equal to ik e to the ikx. Yeah. I'm not, there's nothing up my sleeves, right? So in particular, if I want to get h bar k, I can multiply by h bar and divide by I. Multiply by h bar, divide by I. Derivative with respect to x, e to the ikx. And this is equal to h bar k, e to the ikx. That's suggestive. And I can write this as p, e to the ikx. So let's quickly check the units. Okay. So first off, what are the units of h bar?
All right, what are the units of h bar? You know what, I'm not sure exactly. H bar k. I'm gonna have to go back in the notes to check that. Let's just let him answer it.
Here's the super easy to remember what the units of, or the dimensions of h bar are. Delta x, delta p is h bar.
Oh, okay, so if delta x, delta p are h bar, delta x is the variance in length. I believe that's, let's go back to our notes here. That is the expectation of x squared minus x. I want to say that the delta x is length, but not length. Let's go back to our thing. Is it not length squared minus length? I'm not entirely sure. And then momentum is going to be length times mass. Oh, what is this?
Okay, if you're ever in doubt, if you just can't remember, h bar has units of momentum times length.
Momentum
It's just
times
the
length.
easiest way to remember it. You'll never forget it that way. So if h bar has units of momentum times length, what are the units of k? 1 over length. So does this dimensionally make sense? Yeah. Momentum times length divided by length, number, momentum. Good. So dimensionally we haven't lied yet. Okay. But so this makes it tempting to say something like, well, hell, h bar upon I, derivative with respect to x, is equal in some question mark, quotation marks, p. Right? So at this point, it's tempting to just say, look, trust me, p is h bar upon I dx. But I don't know about you, but I find that deeply, deeply unsatisfying. So let me ask the question slightly differently. We've followed the de Broglie relations, and we've been led to the idea that, and using wave functions, that there's some relationship between the momentum, the observable quantity that you measure with sticks and meters and stuff, and this operator, this differential operator, h bar upon I, derivative with respect to x. By the way, my notation for dx is the partial derivative with respect to x. It's just notation. So if this is supposed to be true in some sense, we have to do with a derivative. Momentum is about velocities, which is like derivative with respect to time, right? Times mass. Mass times derivative with respect to time, velocity. So what does it have to do with the derivative with respect to position? And this ties into the most beautiful theorem in classical mechanics, which is Noether's theorem. Named after the mathematician who discovered it, Noether. And just out of curiosity, how many people have seen Noether's theorem in class? Oh, that's so sad. That's sin. Okay, so here's a statement of Noether's theorem. And it underlies an enormous amount of classical mechanics, but also of quantum mechanics. Noether, incidentally, was a mathematician. There's a whole wonderful story about Noether. Weil went to her and was like, look, I'm trying to understand the notion of energy, and just, this guy down the hall, Einstein, has this theory called general relativity about pair space-time that has something to do with gravity. But it doesn't make a lot of sense to me because I don't even know how to define the energy. So how do you define momentum and energy in this guy's crazy theory? And so Noether, who's a mathematician, did all sorts of beautiful stuff in algebra, looked at the problem and was like, I don't even know what it means in classical mechanics, so what does it really mean in classical mechanics? So she went back to classical mechanics and from first principles came up with a good definition of momentum, which turns out to underlie the modern idea of conserved quantities and symmetries. And it's had an enormous, say her name with praise. So Noether tells us the following statement. To every symmetry, and I should say continuous symmetry, so to every symmetry is associated a conserved quantity. Okay? So in particular, what do I mean by symmetry? Well, for example, translations. X goes to X plus some length L. This can be done for arbitrary length L. So for example, translation by this much or translation by that much. These are translations. To every symmetry is associated a conserved quantity. What symmetry is associated to translations? Conservation momentum, P dot. To time translations, T goes to T plus capital P. What's the conserved quantity associated with time translational symmetry? Energy, which is time dependent. And rotations, rotational symmetries. X as a vector goes to rotations, some rotation, times X. What's conserved by virtue of rotational symmetry? Angular momentum, rock on. Okay. So quickly, I'm not going to prove to you Noether's theorem. It's one of the most beautiful and important theorems in physics, and you should all study it. But let me just convince you quickly that it's true in classical mechanics. And this was observed long before Noether pointed out why it was true in general. What does it mean to have translational symmetry? It means that if I do an experiment here and I do it here, I get exactly the same results. Right? I translate the system and nothing changes. Cool? That's what I mean by saying I have a symmetry. You do this thing and nothing changes. Okay, so imagine I have a particle, a classical particle, and it's moving in some potential. This is U of x, right? And we know what the equations of motion are in classical mechanics from F equals ma. P dot is equal to the force, which is minus the gradient of u, right? That's F equals ma in terms of the potential. Now, is the gradient of u 0? No. In this case, there's a force. So if I do an experiment here, do I get the same thing as doing my experiment here? Certainly not. If the system is not translationally invariant, potential breaks that translational symmetry. What potential has translational symmetry? Yeah, constant. The only potential that has full translational symmetry in one dimension is translation invariant, i.e. constant. Okay? What's the force? 0. 0 gradient. So what's P dot? Yep. Noether's theorem. Solid. Okay? Less trivial is conservation of energy. I claim, and she claims, and she's right, that if the system has the same dynamics at one moment and a few moments later, and indeed any amount of time later, the laws of physics don't change in time, then there must be a conserved quantity called energy. There must be a conserved quantity. And that's Noether's theorem. So this is the first step, but it still doesn't tell us what momentum exactly has to do with a derivative with respect to space. We see that there's a relationship between translations and momentum conservation. But what's the relationship? So let's do this. I'm going to define an operation called translate by L. And what translate by L does is it takes f of x and it maps it to f of x minus L. Okay. So this is the thing that affects a translation. And why do I say that's a translation by L rather than minus L? Well, the point, if you have some function like this and it has a peak at 0, then after the translation, the peak is when x is equal to L. Okay? So just to get this on straight. So define this operation, which takes a function of x and translates it by L, but leaves it otherwise identical. So let's consider how translations behave on functions. And this is really cute. F of x minus L can be written as a Taylor expansion around the point L equals 0. So let's do a Taylor expansion for small l. So this is equal to f of x minus L, derivative with respect to x, of f of x, plus L squared over 2, derivative squared, 2 derivatives of x, f of x, plus dot, dot, right? I'm just Taylor expanding, right? Nothing sneaky. Let's add the next term, actually. Actually, let me do this on a whole new board. All right, so we have translate by L on f of x is equal to f of x minus L is equal to f of x, now Taylor expanding, minus L, derivative with respect to x of f, plus L squared over 2, f, I'm just going to write this as f, well, I'm not giving myself enough space, I'm sorry. F of x minus L is equal to f of x minus L with respect to x of f of x plus L squared over 2 derivatives of x, f of x, minus L cubed over 6, we're just Taylor expanding, derivative cubed with respect to x of f of x, and so on, yeah? But I'm going to write this in the following suggestive way. This is equal to 1 times f of x minus L derivative with respect to x, f of x, plus L squared over 2, derivative with respect to x squared times f of x, minus L cubed over 6, derivative cubed with respect to x, plus dot dot dot. Everybody agree with that? But this is a series that you should recognize, a particular Taylor series for a particular function. It's a Taylor expansion for the exponential e to the minus L derivative with respect to x, f of x. So let's just check to make sure that this makes sense from dimensional grounds. So,
all right, I got to work on my dimensional analysis. I've been not getting these questions right when he poses them. So derivative with respect to x is going to be length. Is it length squared? No.
That's a derivative with respect to x as units of 1 over length.
Oh, 1 over length. Okay.
That's a length, so this is dimensionless, so we can exponentiate it. Now, you might look at me and say, look, this is silly. You've taken an operation like a derivative and exponentiated it. What does that mean? And that is what it means. Okay? So we're going to do this all the time in quantum mechanics. We're going to do things like exponentiate operations. We'll talk about it in more detail, but we're always going to define it in this fashion as this formal power series. Questions?
Operators from one space to another.
Oh, you totally can. But we'll come back to that. We're going to talk about operators next time. Okay. So here's where we are. So from this, what does the derivative with respect to x mean? What does the derivative with respect to x do? Well, the derivative with respect to x is something that generates translations with respect to x through a Taylor expansion. If we had L be arbitrarily small, right? L is arbitrarily small. What is the translation by an arbitrarily small amount of f of x? Well, if L is arbitrarily small, we can drop all the higher order terms, and the change is just L dx. So the derivative with respect to x is telling us about infinitesimal translations. Cool? The derivative with respect to a position is something that tells you or controls or generates infinitesimal translations. And if you exponentiate it, you do it many, many, many times in a particular way, you get a macroscopic finite translation. Cool? So this gives us three things. Translations in x are generated in this sense, are generated by the derivative with respect to x. But through Noether's theorem, translations in x are associated to conservation momentum. So you shouldn't be so shocked. It's really not totally shocking. That in quantum mechanics, where we're very interested in the action of things, not just of positions, but on functions of position, it shouldn't be totally shocking that in quantum mechanics, the derivative with respect to x is related to the momentum in some particular way. Similarly, translations in t are going to be generated by what operation? Derivative with respect to time. So derivative with respect to time, from Noether's theorem, is associated with conservation of energy. That seems plausible. Derivative with respect to, I don't know, an angle, a rotation. That's going to be associated with what? Angular momentum. Okay? But angular momentum around the axis for whom this is the angle, so I'll call that c for the moment. Okay? And we're going to see these pop up over and over again. But here's the thing. We started out with these three principles today, and we've led ourselves to some sort of association between the momentum and the derivative, like this. Okay? And I give you some reason to believe that this isn't totally insane. Translations are deeply connected with conservation of momentum. Translational symmetry is deeply connected with conservation of momentum. And an infinitesimal translation is nothing but a derivative with respect to position. Okay? Those are deeply linked concepts. But I didn't derive anything. I gave you no derivation whatsoever of the relationship between ddx and momentum. Instead, I am simply going to declare it. I am going to declare that in quantum mechanics, you cannot stop me, in quantum mechanics, P is represented by an operator. It's represented by the specific operator, h bar upon I, derivative with respect to x. And this is a declaration. Okay? It is simply a fact. And when I say it's a fact, I mean two things by that. The first is, it is a fact that in quantum mechanics, momentum is represented by derivative with respect to x times h bar upon I. Secondly, it is a fact that if you take this expression and you work with the rest of the postulates of quantum mechanics, including what's coming next lecture about operators and time evolution, you reproduce the physics of the real world. You reproduce it beautifully. You reproduce it so well that no other models have ever vaguely come close to the explanatory power of quantum mechanics. Okay? It is a fact. It is not true in some epistemic sense. You know, you can't sit back and say, oh, a priori, starting with the integers we derive, that P is equal to no. It's a model. But that's what physics does. Physics doesn't tell you what's true. Physics doesn't tell you, what a priori does the world have to look like. Physics tells you, this is a good model, and it works really well, and it fits the data. The degree that it doesn't fit the data, it's wrong. Okay? This isn't something we derive. It's something we declare, we call it our model, and then we use it to calculate stuff, and we see if it fits the real world. Please leave. Thank you. So, I love MIT, I really do. Okay. Okay, so let's leave it. So let me close off at this point with the following observation. We live in a world governed by probabilities. There's a finite probability at any given moment that two pipes might walk into a room. Okay? You just never know. You never know. But those probabilities can be computed in quantum mechanics. And they're computed in the following ways. As we'll study in great detail. If I take a state, psi of x, which is equal to e to the ikx, this is a state that has every moment in h bar k. Right? We claimed this. This was Debray and Davis and Kerr. Note the following. Take this operator and act on this wave function with this operator. What do you get? P hat, well, we already know because we constructed it to have this property. P hat on psi of x, and I'm going to call this psi sub k of x because it has a definite k, is equal to h bar k psi k of x. A state with a definite momentum has the property that when you hit it with the operation associated with momentum, you get back the same function times a constant, and that constant is exactly the momentum we ascribe to that plane wave. Is that cool? Yeah. Good, excellent. So the hat above the P is to remind you that P is not a number, it's an operation. It's a rule for acting on functions. We'll talk about that in great detail next time. But here's what I want to emphasize. This is a state which is, equal to all others in the sense that it's a perfectly reasonable wave function, but it's more equal because it has a simple interpretation, right? The probability that I measure the momentum to be h bar k is 1. The probability that I measure it to be anything else is 0. Correct? But I can always consider the state which is a superposition. Psi is equal to alpha. Let's just do 1 over root 2. E to the ikx, k1x, plus 1 over root 2, e to minus ikx. Okay? K2. Is this state a state this state, I'll call this psi sub s. If I act on this state with the momentum operator.
Yeah, I'll scan my notes later, probably when the class is done.
That's interesting. So it seems to be that if we have a state with definite momentum and we act on the momentum operator, we get back this momentum. If we have a state that's a superposition of different momentum and we act on it with momentum operator, this gives us h bar k1, this gives us h bar k2, so it changes which superposition we're talking about. We don't get back our same state. So the action of this operator on the state is going to tell us something about whether the state has definite value of the momentum. And these coefficients are going to turn out to contain all the information about the probability of the system. This is the probability, when norm squared, that it will measure the system to have momentum k1. And this coefficient, norm squared, is going to tell us the probability that we have momentum k2. So I think the current wave function is something like a superposition of, 1, over 10 psi pirates plus 1 minus 1 over 100 square root to normalize the property psi, no pirates. And I'll leave you with pondering this probability. We'll see you guys next time.
All right, are we, this is a little bit longer. Are we missing something here? I don't know, I think they just have it silent. Okay, so this was the first class where I feel like some math was happening that wasn't, I had to kind of think about when it was happening here. So I'm going to just sort of try to roughly recap what was discussed in the lecture without looking at my notes, and then I'm going to try to go through my notes and explain what I wrote down, because there's some parts that I don't exactly. So if we go back to where this one began, there was a big starting point of this lecture was talking about just sort of recapping what we had discussed in the past. There was some clicker exercise, well, no clicker in the class, I think it was hand raising, about some various questions. I got those right. So we're pretty good on lectures 1 to 3. If I can recall properly what happened in this class, we had Noether's theorems, which are basically showing that any symmetry we see in the universe, so translational symmetry, symmetry in time, symmetry in over rotation, results in a conserved quantity, in which case translational symmetry is conservation of momentum, symmetry of time is conservation of energy, symmetry of rotation is conservation of angular momentum. And then there's also basically, I think we were figuring out, oh, right, we did the definitions of uncertainty, which is essentially standard deviation of the wave function, and expectation, which is again, this is stuff from basic probability. So this stuff I didn't find too difficult. The stuff that was sort of more difficult is we're looking at here. Let me just move this over. Is some of this stuff now we're getting into quantum kind of operators. So let me just see if I got over everything. So there's a recap, and then we talked about expectation. This stuff, I mean, some of the math I'm going to have to like work on some of the ideas like this. Oh, excuse me. I'm bumping my thing here. Oh, there we go. You know what? I even marked out where the notes were for last time, and now I bumped the bumped the thing. So let me just switch over to this here. So now that we're done the thing here. So, well, this is unfortunate that I had this all mapped out so that I wouldn't be off camera, and now I bumped the camera. So, with respect to this thing here, like this kind of stuff where these are things that I probably wouldn't have recalled, but I mean, they do follow from what is being discussed in terms of standard deviation being this is the difference between the squared value and the expected value. The expected value of the squares versus the expected value squared. And this is the standard deviation. And then we have basically some ideas here. I added this one here just because I just wanted to do a little bit of practice in the lecture. He's talking about some notational things. So this is good to pay attention to notation, because that's often, that this means the expectation. That's the kind of thing that would have confused me. Oh, sorry, right here. This is the expectation. That's the kind of thing that would have confused me earlier. And yeah, so we've got that. We have here this is sort of a dubious kind of possibility, because the momentum is not something that's going to be defined for a well-defined position, so we can't really do this. And then we did a little bit of derivation to get this hypothetical operator that basically the momentum should be related to the partial derivative in space of h bar over I. So this was a little bit, again, some dimensional analysis. I think some of this is a little bit, I'm a little bit shaky with this. I'm not quite sure exactly how we got to this sort of point. We were talking about taking the derivative with respect to x of this sort of function. We get ik e to the ikx. And so we do a little bit of flipping around. So momentum is equal to hk. So we want to get this to be hk. So what are we doing here? We take ik. How do they get the h over here? With respect to ikx. Oh, okay. So that if we times this by hi, and then we have this derivative, this, we get h cut k, which is equal to momentum. So this came from waves. So this came from waves and de Broglie. And so we had this before. And then basically we wanted to end up with momentum times this sort of function. So this momentum operator, we hypothesized that it was going to be this, because if we take this here, we get ik. And so we divide by I, so we get rid of the I. And then it would just be hk, which is this momentum. So this idea being that if we get rid of the wave function, this is equal to this. So if we subtract the e to the ikx on both sides, this was sort of the hypothetical thing. The dimensional analysis, which I also didn't get right off the bat of what the dimensions of h are, is show that this is sort of plausible at the very least. And we talked about Noether's theorem, discussed that a little bit. And then we went into discussing this translation operator, Taylor expansion. Okay, so this is something that I do vaguely remember from, I believe this was from Calculus 1. But yeah, you take the function along with its derivatives, and this is a way of approximating any function. So if we don't know what f of x is, you can do this Taylor expansion series to try to get some sort of estimate. And so this this right here, we had this basically we just had this sort of partial derivative. We kind of removed the f of x, and we looked at this is because this is a Taylor expansion of an exponential. So we have the exponentiation of this operator is equal to f of x. So this is something that I'm not, this exponentiated operations is related to Taylor series. So I have to look at this maybe a little bit more. We'll have to see what's going on here, because this e to the minus L dx, or partial derivative of x times f of x, is a little bit confusing right now. But I mean, we'll just sort of try our best when we go to the problem sets. And then, so basically translations in x are created by this partial derivative in x. And so this is how we're getting this kind of relationship. And then this is, he's just sort of saying this. So he's not deriving this from what we know right now, but he's stating that this is the momentum operator. So that if we want to know, we do this, we get the momentum. Yeah, so if we did this, we would get the momentum operator of p to the ex is, we're going to get the momentum operator. So I'm not quite sure what's happening with this momentum operator. I mean, it's not, doesn't seem to be the Fourier transform. So I'm assuming that what we're looking at here is not like this is what it is in momentum space, but I think I need to look a little bit more to figure out what's going on here. So you know what I'm going to do just real quick, because it's going to annoy me if I don't fix it. I'm going to just reposition my camera here and just adjust this masking tape I just put down just to block off where the edge of it is, because I was finding that difficult yesterday. There we go. My goal basically is I just want to avoid, when I'm watching a lecture, doing notes, accidentally being off camera. And this camera is just kind of randomly positioned above the desk here, so there's no real rhyme or reason to it. So I'm going to do this just to preserve my sanity. And then maybe I will look at a few of the questions that some people have been asking. As I mentioned, when I'm doing the lectures, I'm trying to respond to some of the questions if it looks like it's related to the topic. If it's not really related to the topic of what we're discussing, I'm going to be a little bit better about like avoiding answering them during the lecture, but I can try to answer some things once we're done. So someone asked me how to study medicine. I think if you look at an evidence-based guide for studying medicine, that would be a good resource. Just Google that. Someone's asking me whether I'm going to learn big data. I'd like to learn machine learning and that kind of stuff later. One thing at a time, though. And another person's asking me whether I'm going to scan my notes. I'm going to try to scan the notes after, but I don't think I'm going to do it in the interim just because I think it's going to be too time consuming to do it every single day. And then, are we expected to study with you like you are teaching? So I'm not teaching this class, I'm learning it. And the idea for this was to showcase what my process is for handling a class like this. So I'm not, I don't think this is the ideal format for learning it. If you wanted to learn it, probably the easiest thing would be to do it yourself on the class. But you can follow along with me for sure. And I mean, if you were learning this, this could be like you're learning with me. Otherwise, you could just sort of see how I'm tackling classes and approach it that way. So overall, there's stuff that I'm a little bit shaky about from this last lecture. I mean, I think the main thing that I'm not 100% confident with here is this whole exponentiated operators, Taylor series link that's happening. I'm not entirely clear on what this momentum operator is doing, but I think we'll probably learn a little bit more and it'll be a little clearer as we do more lectures. So I'm going to move right into the next lecture. Again, our goal was to get to lecture 10, hopefully by Wednesday, and then we can start doing problem sets. And that's really where the rubber is going to hit the road, so to speak. So let's go straight into it.
The following content is provided under.
All right, we're going quite fast there. So this one is not Alan Ebbs. This one's going to be Barton Zwiebach. So let me just get this here. All right. Oh, someone asked me about textbooks. I do have a textbook. This one here, Quantum Physics, French and Taylor. I don't know how much I'm going to be using it, but I will mention if I use a textbook. I just got it just as a backup.
Creative Commons license. Yours. Continue to offer high-quality educational resources for free. To make a donation or review additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at postw.mit.edu.
Today, we're going to just continue what Alan Adams was doing. He's away in a trip in Europe, so he asked me to give the lecture today, and we'll just follow what he's told me to do. He was sort of sad to give me this lecture. This is one of the most interesting ones. It's the one where you get to see the Schrodinger equation. But anyway, had to be away, so we'll do it here. He also told me to take off my shoes, but I won't do that. So let's go ahead. So what do we have so far? It's going to be a list of items that we have. And what have we learned? We know that the particles or systems are governed by wave functions, described by wave functions. Wave functions. And those are psi of x. And these are complex numbers, belong to the complex numbers, and they're continuous and normalizable. Their derivatives need not be continuous, but the wave function has to be continuous. It should be also normalizable, and those are two important properties of it, continuous and normalizable. Second, there's a probability associated with this thing, and this probability is described by this special p of x. And given that x is a continuous variable, you can't say, well, what is the probability that the particle is just at this point? It would be 0 in general. You have to ask typically, what's the probability that I find it in a range? It's a continuous variable that's postulated to be given by the square of the wave function and the x. Third, there's superposition.
This is just recapping, so I'm going a little faster.
So particles can be in superposition. So a wave function that depends on x may quickly or generally be given as a superposition of two wave functions. And this is seen in many ways. You have these boxes of particles, a superposition at top and side and hard and soft, and photon superposition of linearly polarized here or that way. That's always possible to explain. Now, in addition to this, to motivate the next one,
we talk about relations between operators. There was an abstraction going on in this lecture, in the previous, in this course, in the previous lectures, in which the idea of the momentum of a particle became that of an operator on the wave function. So we've been, so as an aside, operators, momentum. We have that the momentum of a particle has been associated with an operator, h bar over I dx. Now, two things here. My taste, I like to put h bar over I. Alan likes to put I h bar. That's exactly the same thing, but no minus signs is a good thing, in my opinion, so I avoid that when possible. Now, there's ddx here, it's a partial derivative, and there seems to be no need for partial derivatives here. Why partial derivative? I only see functions of x. Anybody? Why? Yes. Complete wave function depends on time as well. Yes, exactly. That's where we're going to get to today. This is the description of this particle at some instant. So we didn't put the time. The time here is implicit. It could be at some time, now, later, sometime, but that's all we know. So in physics, you're allowed to ask the question, well, if I know the wave function at this time, and that seems to be what I need to describe the physics, what will it be later? And later time will come in. So therefore, we'll stick to this partial ddx here. All right. So how do we use that? We think of this operator as acting on the wave functions to give you roughly the momentum of the particle, and we've made it in such a way that when we talk about the expectation value of the momentum, the expected value of the momentum of the particle, we compute the following quantity. We compute the integral from minus infinity to infinity dx. We put the conjugate of the wave function here, and we put the operator h bar over I ddx acting on the wave function here.
Okay, whoa, all right. Let's just jot this down because this is new, I believe. Dx, we've got the complex conjugate. H bar over I. I'm going to do Alan's notation here for ddx. It's just dx. Okay.
And that's supposed to be sort of like saying that this evaluates the momentum of the wave function. Why is that so? It is because if you try to say, oh, any wave function, a general wave function, need not be a state in which the particle has definite momentum. So I cannot just say the momentum of a particle is the value of this operator on the function. Because if I act with this operator on the function, on the wave function, it might not return me the wave function. In fact, in general, we've seen that for special wave functions of the form psi, a number, e to the I k x, then p, let's think p hat as the operator on psi would be h bar over I ddx on psi gives you what? Well, this h over I, the h remains there. When you differentiate with respect to x, the ik goes down and the I cancels, so you get hk times the same wave function. And for this, we think that this wave function is a wave function with momentum hk. Because if you act with the operator p on that wave function, it returns for you hk. So we think of this as has p equal hk, h bar k. So the thing that we want to do now is make this a little more general. This is just talking about momentum, but in quantum mechanics, we're going to have all kinds of operators.
So I just want to kind of pause this because we're now getting into some difficult stuff here. You notice I slowed it down to 1 speed. So I'm going to try to explain how I'm seeing this right now, is that it looks like what we were doing in the last lecture is that we just took this wave that has a defined momentum. So we know it has a defined momentum because of the de Broglie relations, which say that a wave, particularly let's say any kind of wave, it has momentum equals to this h bar k being the wave number, and this being Planck's constant. There might be a factor of 2 pi there. I might be getting that wrong. But so this we know from de Broglie. So this is Broglie's de Broglie. I don't know how to say it. Broglie's relation. This is what we know for this. So in the last class, where I was a little confused, we have this e to the ihk. Was it e to the ihk? E to the ikx. Sorry, e to the ikx, or k is the wave number. And so if we have this sort of function, we know that what the momentum is. We know that this is the momentum of this is equal to hk. Because we know that the momentum is equal to hk, then the idea being that perhaps the way of taking this to hk is a general procedure for getting momentum off of the wave function. And so we did a little bit of, in the last class, we did a little bit of derivation here. And then that was, well, what if we took the derivative with respect to the x, we dropped down the ik, so it's ik e to the ikx. So if we took h bar over I d to the ikx, we'd get rid of the I, we'd add the h bar, and we would get h bar k plus the wave function. So the idea being that this h bar I d to the x would be the momentum, so to speak. And we found that that fit units, and we had some idea that this was going to make sense, and then we stated it. So now what we're seeing is that this was sort of the temporary example. I think what he's going to do next is explain, kind of rigorously justify why this is the right way to do this, because this was just an example that was taken. It wasn't a, proof that for all functions this is the right way to get the momentum.
So we need to be more general. So this is going to be, as Alan calls it, a math interlude. Based on the following question: what is an operator? And then the physics question: what do measurable things have to do with operators? So, about operators and measurable things. Quantities. Now, your view of operators is going to evolve. It's going to evolve in this course, it's going to evolve in 805, it probably will continue to evolve. So we need to think of what operators are. And there is a simple way of thinking of operators that is going to be the basis of much of the intuition. It's a mathematical way of thinking of operators, and we will sometimes use it as a crutch. And the idea is that basically operators are things that act on objects and scramble them. So whenever you have an operator, you really have to figure out what are the objects you're talking about. And then the operator is some instruction on how to scramble this object. So for example, you have an operator, you must say what it does to any object here. The operator acts on the object and gives another object. So in a picture, you have all kinds of objects, sets, a set of objects, and the operators are things. You can have a list of operators, and they come here and move those objects, scramble them, do something to them. And we should distinguish them because the objects are not operators and the operators are not objects. So what is the simplest example in mathematics of this thing? Is vectors and matrices. Simplest example. Objects are vectors, operators are matrices. And how does that work? Well, you have a 2 by 2 the case where you have a set in which you have vectors with 2 components. So example, a vector that has 2 components, v1 and v2, and the matrices, this is the object.
Are we at 1.5 already? Yeah.
A matrix, a11, a12, a21, a22, as an operator, and m on a vector is a vector. If you add with a matrix on a vector, this 2 by 2 matrix on this column vector, you get another vector. Simplest example of operators acting on objects. In our case, we're going to talk about we're going to have to begin in quantum mechanics, we're going to begin with a more sophisticated one, in which the objects are going to be going to be functions. In fact, I will write complex functions of x. So let's see the list of operators. And what do the operators do? The operators act on functions. So what is an operator? It's a rule on how to take any function, and you must give a rule on how to take from that function another function. So let's start with an example. It's probably the easiest thing to do. So an operator acts on the functions. So an operator for any function f of x will give you another function.
So I mentioned this when I was going over the problem sets, but I think it's worth restating that my analogy for this is when you're doing programming, you can make functions that take functions and spit out another function. So you can write in programming, you can like say, you know, like iterated, and then you can have as a function, let's say, you know, square root, and then you can take like 3, and then you can get it to return, you know, some sort of like 4i equals 3, then, you know, square root of x, you know, it saves a thing. So basically what you can do is you can return some kind of function that does this. So this sort of idea of taking like a function and turning it into another function, returning that function, this is something from programming. So this is something that I kind of, I already have some familiarity with, and that's my analogy going forward with this. Although, of course, this is mathematical.
And here's operator O. We put a hat sometimes for operators. So the simplest operator, the operator 1. We always, mathematicians love to begin with trivial examples. Sometimes they'll illustrate anything almost, and just can confuse you many times. But actually, it's good to get that out of the way. So what is the operator 1? One possibility. It takes any function and gives you the number 1. Do you think that's it? Who thinks that's it? Nobody. Very good. That definitely is not a good thing to do, to give you the number 1. So this operator does the following. I will write it like that. The operator 1 takes f of x and gives you what? F of x, correct. Good. So it's a very simple operator, but it's an operator. It's like what matrix? Like an identity matrix. Very good. There could be a 0 operator that gives you nothing and would be a 0 matrix. So let's write the more interesting operator. The operator ddx. That's interesting. The derivative can be thought of as an operator because if you start with f of x, it gives you another function, ddx of f of x. And that's a rule to get from one function to another. Therefore, that's an operator. Qualifies as an operator. Another operator that typically can confuse you is the operator x. X, an operator. What does that mean? Well, you just have to define it. You know, at this moment, it could mean many things. But you will see that what I'll write is the only thing that probably makes some sense. So what is the operator x? Well, it's the operator that given f of x gives you the function x times f of x. That's a reasonable thing to do. It's multiplied by x. It changes the function. You could define the operator x squared that multiplies by x squared. And the only reasonable thing is to multiply it by. You could divide by it, and you may need to divide by it as well. And you could define the operator 1 over x that gives you the function that's 1 over x. We will need that sometime, but not now. Let's see another set of operators. So we give a name. It doesn't have a name because it's not all that useful, in fact. But it's good to illustrate. Think the operator s sub q for square, sq for the first 2 letters of the word square, that takes f of x into f of x squared. That's another function. You could define more functions like that. The operator p42. That's another silly operator. Well, certainly a lot more silly than this one. That's not too bad. But the p42 takes f of x and gives you the number 42. That's the constant function. So that's a function of x. It's a trivial function of x. Well, enough examples. So you get the idea. Operators act on functions and give you functions, and we just need to define them, and then we know what we're talking about. Yes?
Is the Dirac delta an operator?
The Dirac delta, well, you can think of it as an operator. So it all depends how you define things. So how could I define the Dirac delta function to be an operator? So delta of x, can I call it the operator delta hat of a? Well, I would have to tell you what it does for functions. And probably I would say delta hat of a function of x, is equal to delta of x minus a. That's a function of x. And that's it. It's an operator. Now the question is it a useful operator? And sometimes it will be useful, in fact. This is a more general case of another operator. Maybe I could define O sub f, O sub h of x, is the operator that takes f of x into h of x times f of x. So that would be another operator. Now, there are operators that are particularly nice, and there are the so-called linear operators. So what is a linear operator? is one that respects superposition. So linear operator respects superposition. So O hat is linear. O hat is linear. It's a linear operator. If O hat on A times f of x plus b times g of x, that's what you would imagine it should do. It acts on the first and it acts on the second. Acting on the first, the number goes out and it doesn't do anything, say, on the number. It's linear, it's part of that idea. And it gives you O on f of x plus b times O on g of x. So your operator may be linear or it may not be linear. And we have to just test them. And
This is very related to linear algebra.
The list of operators that we have, let's see. 1, ddx, x, how much, which one? SQ, P42, and O sub h of x. Let's see. Let's vote for each one, whether it's linear or not. A shouting match, whether I hear a stronger yes or no. Okay, 1 is a linear operator, yes? No? Yes. All right. ddx, linear, yes?
Yes.
Good. That's strong enough. Don't need to hear the other one. X hat, linear operator, yes or no?
Yes.
Good. Squaring, linear operator?
No.
No way it could be a linear operator. It just doesn't happen. If you have SQ on f plus g, it would be f plus g squared, which is f squared plus g squared plus, unfortunately, to fg. And this thing ruins it because this is SQ of f plus SQ of g. It's even worse than that. You put SQ on AF. By linearity, it should be a times the operator, but when you square a times f, you get a squared, f squared. So it's we don't even need two functions to see that it's not real. So definitely no. How about P42? No, of course not, because if you add two functions, it still gives you 42, it doesn't give you 84. So no. How about OH of x? Yes, it does that. If you add with this operator on a sum of functions, this distributive law, it works, so this is linear. Good. Linear operators are important to us because we have superposition of allowed states. So if this is a state and this is a state, this is also a good state. So if we want...
Is convolution an operator?
Well, in our theory, we want linear operators. So that's good. So we have those linear operators. And now operators have another thing that makes them sometimes special. It is the idea that they're simpler objects they can act on. We don't assume you've studied linear algebra in this course, so whatever I'm going to say, take it as motivation.
No, there's no linear algebra? Oh,
At some
okay.
stage. You will need a little more linear algebra in 805, but at this moment, just basic ideas. So whenever you have matrices, one thing that people do is to see if there are special vectors. Any arbitrary vector, when you act it with a matrix, is going to just jump and go somewhere else, point in another direction. But there are some special vectors that you act. If you have a given matrix M, there are some
Eigenvectors
sometimes that acted by M remain in the same direction. They might grow a little or become smaller, but they remain in the same direction. These are called eigenvectors. And that constant of proportionality, proportional to the action of the operator on the vector, is called the eigenvalue. So these things have generalizations for our operators. So operators can have special functions, eigenfunctions. Eigenfunctions. What are these eigenfunctions? So let's consider the operator A hat. It's some operator, I don't know which one of these, but we're going to talk about linear operators. So linear operators don't have eigenfunctions. A hat. So A hat, there may be functions that when you add with the operator, you sort of get the same function up to possibly a constant A. So you may get A times the function. And that's a pretty unusual function because on most functions, any given operator is just going to make a mess out of the function. But sometimes it does that. So to label them better, with respect to the operator A, we put the subscript A, which means that there's some special function that has a parameter A for which this operator gives you A times that special function. And that special function is called, this is the eigenfunction, and this is the eigenvalue. And that eigenvalue is a number. It's a complex number. Let's see, letter over there. So these are special things. They don't necessarily happen all the time to exist, but sometimes they do, and then they're pretty useful. And we have one example of them that is quite nice. For the operator A equal P, we have eigenfunctions e to the ikx with eigenvalue hk. So this is a connection to this whole thing. We wanted to make clear for you that what you saw here, that this operator acting on this function gives you something times this function, is a general fact about operators. Operators have eigenfunctions. So the eigenfunction e of x with eigenvalue hk, because indeed p hat of this e to the ikx, as you've seen, is h bar.
No, I only went up to 802. I didn't do it 803 or this one 804.
This is the function labeled a would be like k. Here is something like k again, and here is this thing. But the main thing, operator on the function number times the function is an eigenfunction. Yes? Well, for a given operator, good question, A is a list of values. So there may be many, many, many eigenfunctions. In many cases, infinitely many eigenfunctions. In fact, here I can put for k any number I want, and I get a different function. So A is belong to C and may take many or even infinite values. If you remember, for nice matrices, n by n matrix, meaning a nice n by n matrix has n eigenvectors and eigenvalues that sometimes are degenerate, sometimes the eigenvalues are this. So, okay, linearity is the sum of two eigenvectors and eigenvector. Yes? No? No, no. Correct. That's not necessarily true. If you have two eigenvectors, they have different eigenvalues, so things don't work out well necessarily. So an eigenvector plus another eigenvector is not an eigenvector. So you have here, for example, A f1 equal A1 f1, and A f2 equal A2 f2, and A on f1 plus f2 would be A f1 plus A1 f1 plus A2 f2, and that's not equal to something times f1 plus f2. It would have to be something times f1 plus f2 to be an eigenvector. So this is not necessarily an eigenvector. And it doesn't help to put a constant in front of here. Nothing helps. There's no way to construct an eigenvector from two eigenvectors by adding or subtracting. The size of the eigenvector is not fixed either. If f is an eigenvector, then 3 times f is also an eigenvector. And we call it the same eigenvector. Nobody would call it a different eigenvector. No, it's really the same. Okay, so how does that relate to physics? Well, we've seen it here already that one operator that we've learned to work with is the momentum operator and has those eigenfunctions. So back to physics. We have other operators, and therefore we have the p operator, that's good. We have the x operator, that's nice, it's a multiplication by x. And why do we use it? Because sometimes we have the energy operator. And what is the energy operator? The energy operator is just the energy that you've always known, but think of it as an operator. So how do we do that? Well, what is the energy of a particle? We've written p squared over 2m plus v of x. Well, that was the energy of a particle, the momentum square over 2m plus v of x. So the energy operator is hat here, hat there.
This is okay. Let's just understand what has just been said here, because I think it's important. Otherwise, I'm going to miss it. So we have p hat squared over 2m plus v of x hat. So this is kinetic energy, and this is potential energy. So this is why this is equal to energy. And how is this equal to kinetic energy? Well, momentum is velocity times the mass. And so we've got this momentum operator, which is giving us the momentum. So this is momentum is, what is this? Velocity times the mass divided by the mass. This is canceling. So it's, what is it? 1/2 v squared. So hold on a sec, 1/2 mv squared. So, oh, sorry, hold on. This is squared. So these are both squared. So we get rid of one of the m's, and then we get this 1/2 mv squared. So that's equal to the kinetic energy. And this right here is some potential function. So if we're on like a hill, let's say, we have more potential energy here than we do when we have here. So this is just some arbitrary function. And it's, I'm not sure why this is an x operator. So, okay, I'll just put that as a flag. So why is this x hat? Like, why is it not v hat or something. Okay, so I'm not sure about that yet.
And now it becomes an interesting object. This energy operator will be called E hat. It adds some functions. It is not a number. The energy is a number, but the energy operator is not a number. Far from a number, in fact. The energy operator is minus h squared over 2m d second dx squared.
Oh.
Why that? Well, because p was h bar over I dx.
Let's get back.
This sort of arrow here, it's sort of an introduction.
Wait till the camera gets back.
You just say p hat is h bar over I dx. End of story. It's not like double arrow. It's just what it is, that operator. That's what we call it. So when we square it, the I squares you get a minus h squares, and ddx applied twice is the second derivative. And here we get v of x hat, which is your good potential. With
okay, here we go. So the energy operator is h squared over 2m d squared d x squared plus whatever potential we have.
Whatever potential you're interested in which whenever you see an x, you put an x hat. And now this is an operator. So you see, this is not a number, not a function. It's just an operator. The operator has this sort of operator v of x. Now, what is this v of x here as an operator? This v of x as an operator is just multiplication by the function v of x. You see, you have here that the operator x is f of x like that. I could have written the operator x hat to the n. What would it be? Well, if I act on a function, this is a lot of x hats acting on the function. Well, let the first one add, you get x times f of x. The second adds another x. So this is just x to the n times f of x. So lots of x hats to the 100 on a function is just x to the 100 times the function. So v of x on a function is just v of the number x on a function. It's just like this operator, all in which you multiply by a function.
Oh, so this is just notational then. So I'm just going to scratch this off because this is just a notation.
So please, I hope this is completely clear what this means as an operator. You take the wave function, take two derivatives, and add the product of the wave function times v of plane x. So I'll write it here, maybe. So important. E hat on psi of x is therefore minus.
All right, let's just do it again.
H squared over 2m d second dx squared of psi of x plus just plain v of x times psi of x. That's what it does. That's an operator. And for these operators, in general, so we're math interlude. Is it over? Not quite. Wow. No, yes.
All right, I'm going to rewrite that. It's a little messy.
So here is, I'll say something more here, but it's going to be over now. Our 3 continues here then with 4. 4 to each observable, we have an associated operator. So for momentum, we have the operator p hat. And for position, we have the operator x hat. And for energy, we have the operator e hat. And these are examples of operators. Some operator a hat. Can be any of those. And there may be more observables depending on the system you're working in. If you have particles on a line, there's not too many more observables at this moment. If you have a particle in general, you have angular momentum. That's an interesting observable. There can be others. So for any of those, our definitions, just like we did for momentum, the expectation value of the operator is computed by doing what you did for momentum. You add with the operator on the wave function here and multiply by
Oh, so I think this is why we're getting that. Remember this from earlier. Well, this is what this form takes.
The complex conjugate function and integrate. Just like you did for momentum. This is going to be the value that you expect after many trials on a on this wave function, you would expect that the measured value of this would exhibit a distribution in which its expectation value, the mean, is given by this. Now, there are other definitions of, one definition that already has been mentioned is that the uncertainty of the operator on the state psi, the uncertainty, is computed by taking the square root of the expectation value of A squared minus the expectation value of A as a number squared. Now, the expectation value of A squared, just simply here instead of A, you put A squared, so you put A squared here. That, unless the function is very special, that's very different and always bigger than the expectation value of A squared. So this is a number, and it's called the uncertainty, and that's the uncertainty of the uncertainty principle. So for operators, we need to have another observation that comes from matrices that is going to be crucial for us, is the observation that operators don't necessarily commute. And we'll do the most important example of that. So we'll try to see if the operators associated with our momentum and position commute. And what do we mean by commute or don't commute? Whether the order of multiplication matters. Now, we talked about matrices at the beginning, and we said matrices have them vectors to give you vectors. So do they commute? Well, matrices don't commute. The order matters for matrix multiplication. So these operators we're inventing here for physics, the order does matter as well. So commutation. So let's try to see if we compute the operator P and X hat, is it equal to the operator X hat times P? This is a very good question. These are two operators that we've defined, and we just want to know if the order matters or it doesn't matter. So how can I check it? I cannot just check it like this, because operators are only clear what they do is when they act on functions. So the only thing that I can do is test if this thing acting on functions give the same. So I'm going to act with this on the function f of x, and I'm going to act with this on the function f of x. Now, what do I mean by acting with p times x hat on the function f of x? This is by definition. You act first with the operator that is next to the f, and then with the other. So this is p hat on the function x hat times f of x. So here I would have, this is x hat on the function p hat f of x. So if you have a series of matrices, m1, m2, m3, acting on a vector, what do you mean? Act with this on the vector, act with this on the vector, and with this. That's multiplication. So we're doing that. So let's evaluate. What is x operator on f of x? This is p hat on x times f of x. That's what the x operator on the function is. Here, what is x hat? And now I have this. So I have here h over I b dx of f. Let's go one more step here. This is h over I b dx now of this function, x f of x. And here I have just the x function times this function. So h over I x df dx. Well, are these the same? No, because this ddx here is not only acting on f like here, it's acting on the x. So this gives you two terms. One extra term of the ddx acts on the x, and then one term that is equal to this. So you don't get the same. So you get from here h over I f of x, from you after the x, plus h over I x df dx. So you don't get the same. So when I subtract them, so when I do xp minus px acting on the function f of x, what do I get? Well, I put it in this order, x before the p. It doesn't matter which one you take, but many people like this. Well, this term's cancelled, and I get minus this thing. So I get minus h over I f of x, or I h bar f of x. Wow. You got something very strange. The x times p minus p times x gives you a number, an imaginary number even worse, times f of x. So from this, we write the following. We say, look, operators are defined by the action on function, but for any function, the only effect of xp minus px, which we call the commutator of x with p, this definition, the bracket of two things of ab, is defined to be ab minus ba. It's called the commutator. xp is an operator acting on f of x, gives you I h bar times f of x. So our kind of silly operator that does nothing has appeared here, because I could now say that x hat with p is equal to I h bar times the unit operator. Apart from the Schrodinger equation, this is probably the most important equation in quantum mechanics. It's the fact that X and P are incompatible operators, as you will see later. They don't commute. Their order matters. What's going to mean is that when you measure one, you have difficulties measuring the other. They interfere. They cannot be measured simultaneously. All those things are encapsulated in a very lovely mathematical formula, which says that this is the way these operators work. Any questions? Yes.
See, when X, the commutator of X and P is itself an operator, right?
Right.
So is that what we're saying? That when we had operators before, we can't simply just cancel the f of X. I mean, we're not really canceling it, but is it just because I is part of the only eigenvalue of the operator?
Well, basically, but we've shown by this calculation is that this operator, that this combination is really the same as the identity operator. That's all we've shown. That some particular combination is the identity operator. Now, this is very deep, this equation. In fact, that's the way Heisenberg invented quantum mechanics. He called it matrix mechanics because he knew that operators were related to matrices. It's a beautiful story how he came up with this idea. It's very different from what we're doing today, that we're going to follow Schrodinger today. But it basically, his analysis led very quickly to this idea. And this is deep. Why is it deep? Depends who you ask. If you ask a mathematician, they will probably tell this equation that this is a scary equation. And why is it scary? Because whenever mathematicians see operators, they want to write matrices. So the mathematician is showing this equation, will say, okay, let me try to figure out which matrices you're talking about. And this mathematician will start doing calculations with 2 by 2 matrices and say, no, I can't find 2 by 2 matrices that behave like these operators. I can find 3 by 3 matrices either, and 4 by 4, and 5 by 5. And there's no matrix really can do that, except if the matrix is infinite dimensional. Infinite by infinite matrices. So that's why it's very hard for a mathematician. Now, this is the beginning of quantum mechanics. This looks like a trivial equation, and mathematicians get scared by it. You show them, for physicists, there will be angular momentum. The operators are like this, and it's complicated. E to the I, J, K, L, K. The 3 components of angular momentum have this commutation relation, and H bar here as well. Complicated. 3 operators, they mix with each other. Show it to a mathematician, it starts laughing at you. This is the best, the simplest case. This is easy. This is complicated. It's very strange, but the reason this is easy, the mathematician goes and after 5 minutes comes to you with 3 by 3 matrices that satisfy this relation. And here there weren't. And 4 by 4 that satisfy, and 5 by 5, and 2 by 2, and all of them. You can calculate all of them for you. But this one needs infinite dimensional matrices, and it's very surprising, very interesting, and very deep. All right, so we move on a little bit more to the other observables. So after this, we have more general observables. So let's talk a little about them. That's another postulate of quantum mechanics that continues with this one, postulate number 5. So once you measure, upon measuring an observable A associated with the operator A hat, 2 things happen. You measure this quantity. That could be momentum, could be energy, could be position, you name it. The measured value is must be a number, is one of the eigenvalues. Values of A hat. So actually those eigenvalues, remember the definition of the eigenvalues, it's there. I said many, but whenever you measure, the only possibility is that you get this number. So you measure the momentum, you must get this hk, for example. So observables, we have an associated operator, and the measured values are the eigenvalues. Now, these eigenvalues, in order to be observable, they should be real numbers, and we said, oh, they can be complex. Well, we will limit the kind of observables to things that have real eigenvalues, and these are going to be called later on Hermitian operators. At this moment, the notes say don't mention them. You're going to get them confused. so anyway, special operators that have real eigenvalues, and so we'll mention here they will have to be real. Have to be
Hermitian.
real. And then the second one, which is an even stranger thing that happens, is something you've already seen an example. After you measure, the whole wave function goes into the state, which is the eigenfunction of the operator. So after measurement, system collapses into psi A. The measured value is one of the eigenvalues A of A, and the system collapses into psi A. So psi A is such that A hat psi A is A psi A. So This is the eigenvector with eigenvalue A that you measured. So after you measure the momentum and you found that it's h bar k, the wave function is the wave function of momentum h bar k. If at the beginning it was a superposition of many, as Fourier told you, then after measuring, if you get one component of momentum, that's all that is left of the wave function. It collapses. This collapse is a very strange thing, and it's something about quantum mechanics that people are a little uncomfortable with, and I'm trying to understand better, but surprisingly, nobody has understood it better after 60 years of thinking about it, and works very well. It's a very strange thing, because, for example, if you have a wave function that says your particle is can be anywhere, after you measure where it is, the whole wave function becomes a delta function at the position that you measured. So everything on the wave function, when you do a measurement, basically collapses, as we will say. Now, for example, let's do an example. Position. So you have a wave function, psi of x. You measure, and find the particle at x0. Measure, and you find the particle at x0. So, measure what? I should be clear. Measure position. So we said two things. The measured value is one of the eigenvalues of A, and after measurement, the system collapses to eigenfunctions. Now, here we really need a little of your intuition. A position eigenstate is a particle localized at one place. What is the best function associated to a position eigenstate? It's a delta function, the function that says it's at some point and nowhere else. So the eigenfunctions, delta of x minus x0, it's a function, as a function of x. It peaks at x0, and it's 0 everywhere else. And this is, when you find a particle at x0, this is the wave function. The wave function must be proportional to this quantity. Now, you can't normalize this wave function. It's a small complication, but we shouldn't worry about it too much. Basically, you really can't localize a particle perfectly. So that's the little problem with this wave function. You've studied how you can represent delta functions as limits, and probably intuitively, those limits are the best things. But this is the wave function. So after you measure the system, you go into an eigenstate of the operator. Is this an eigenstate of the x operator? What a strange question. But it is. Look, if you put the x operator on delta of x minus x0, what is it supposed to do? It's supposed to multiply by x. So it's x times delta of x minus x0. If you had a little experience with delta functions, you know that this function is 0 everywhere except when x is equal to x0. So this x can be turned into x0. It just never, at any other place it contributes. This x really can be turned into x0 times delta of x minus x0. Because delta functions are really used to do integrals. And if you do the integral of this function, you will see that you get the same value as the integral of this function. So then you have it. The operator acting on the eigenfunction is a number times this. So these are indeed eigenfunctions of the x operator. And what you measured was an eigenvalue of the x operator, eigenvalue of x. And this is an eigenfunction of x. We can do the same with the momentum. Eigenvalues and eigenfunctions, we've seen them more properly. Now, we'll go to the sixth postulate. The last postulate that we want to talk about is the one of general operators and general eigenfunctions and what happens with them. So let's take now our operator A and its eigenfunctions that can be found. So 6. Given an observable A hat and its eigenfunctions, phi A of x. So an A runs over many values. Okay, so let's consider this case. Now, the eigenfunctions of an operator are very interesting objects. You see, the eigenfunctions of momentum were of this form, and they allow you to expand via the idea of Fourier any wave function as superpositions of these things. Fourier told you can expand any function in eigenfunctions of the momentum. Well, the result is more general. For observables in general, you can expand functions, arbitrary functions, in terms of the eigenfunctions. Now, for that, remember, an eigenfunction is not determined up to scale. You multiply by 3, it's an eigenfunction still. So people like to normalize them nicely, the eigenfunctions. You construct them like this, and you normalize them nicely. So how do you normalize them? Normalize them by saying that the integral over x of psi a star of x, psi b of x, is going to be what? Okay, basically what you want is that these eigenfunctions be basically orthogonal, each one orthogonal to the next. So you want this to be 0 unless these two different eigenfunctions are different, and when they are the same, you want them to be just like wave functions, that their total integral of psi squared is equal to 1. So what you put here is delta AB. Now, this is something that you can always do with eigenfunctions. It's proven in mathematics books. It's not all that simple to prove, but this can always be done. And when we need examples, we'll do it ourselves. So, given an operator that you have its eigenfunctions like that, two things happen. One, can expand psi as psi of x, any arbitrary wave function as the sum, and or sometimes an integral. So some people like to write this and put an integral on top of that. You can write it whichever way you want, it doesn't matter, of coefficients times the eigenfunctions. So just like any wave could be written as Fourier coefficients and these Fourier functions, any state can be written as superposition of these things. So that's one. And two, the probability of measuring A hat and getting A. So A is one of the particular values that you can get. That probability is given by the square of this coefficient, CA squared. So this is P, the probability to measure in psi and to get A. And I think, actually, let's put an A0 there. So here we go. So it's a very interesting thing. Basically, you expand the wave function in terms of these eigenfunctions, and these coefficients give you the probabilities of measuring these numbers. So we can illustrate that again with the delta functions, and we'll do it quick because we get to the punchline of this lecture with the Schrodinger equation. So what do we have? Well, let me think of the operator x example. Operator x, the eigenfunctions are delta of x minus x0 for all x0. These are the eigenfunctions. And we'll write a sort of a trivial equation, but it sort of illustrates what's going on. Psi of x as a superposition over an integral over x0 of delta of x minus x0. I'll write the psi of x0 delta of x minus x0 over like this. Okay, first let's check that this makes sense. Here we're integrating over x0. X0 is the variable. This thing shoots and fires whenever x is equal to x, whenever x0 is equal to x. Therefore, the whole result of that integral is psi of x. It's a little funny how it's written because you have x minus x0, which is the same as delta of x0 minus x. It's just the same thing. And you integrate over x0 and you get just psi of x. But what have you achieved here? You've achieved the analog of this equation, in which these are the psi a's, these are the coefficients, CA's, and this is the sum, this integral. So there you go. Any wave function can be written as the sum of coefficients and the eigenfunctions of the operator. And what is the probability to find the particle at x0? Well, it's from here, the coefficient CA squared. That's exactly what we had before. So this is getting basically what we want. So this brings us to the final stage of this lecture, in which we have to get the time evolution finally. So how does it happen? Well, it happens in a very interesting way. So maybe I'll call it 7, Schrodinger equation. So, as with any fundamental equation in physics, there's experimental evidence, and suddenly, however, you have to do a conceptual leap. You know, experimental evidence doesn't tell you the equation. It suggests the equation, and it tells you probably what you're doing is right. So what we're going to do now is collect some of the evidence we had, and look at an equation, and then just have a flash of inspiration, change something very little, and suddenly that's the Schrodinger equation. Alan told me that, in fact, students sometimes are disappointed that we don't derive the Schrodinger equation. Now let's derive it mathematically. But you also don't derive Newton's equations, F equal ma. You have an inspiration, you get it, Newton got it, and then you use it and you see it makes sense. It has to be a sensible equation, and you can test very quickly whether your equation is sensible. And you can't quite derive it. In 805, we come a little closer to deriving the Schrodinger equation, which is saying unitary time evolution, something that I haven't explained what it is, implies the Schrodinger equation. And that's a mathematical fact that you can begin unitary time evolution, define it, and you derive the Schrodinger equation. But that's just saying that you substituted the Schrodinger equation by saying there is unitary time evolution. The Schrodinger equation really comes from something a little deeper than that. Experimentally, it comes from something else. So how does it come? Well, you've studied some of the history of this subject, and you've seen that Planck postulated quantized energies in multiples of h bar omega. And then came Einstein and said, look, in fact, the energy of a photon is h bar omega. And the momentum of the photon was h bar k. So all these people, starting with Planck and then Einstein, understood what the photon is. The quantum of photons, for photons, you have E is equal to h bar omega, and the momentum is equal to h bar k. I write them as a vector because the momentum is a vector, but we also write them in this course P equal h bar k, assuming you move just in one direction. And that's the way it's been written. So this is the result of much work, beginning by Planck, Einstein, and Compton. So you may recall, Einstein said in 1905 that there seemed to be this quantum of light that carry energy h omega. Planck didn't quite like that. And people were not all that convinced. Experiments were done by Millikan in 1915, and people were still not quite convinced. And then came Compton, and did Compton scattering, and then people said, yeah, these seem to be particles, no way out of that. And they satisfied such a relation. Now, there was something about this that was quite nice, that these photons are associated with waves, and that was not too surprising, because people understood that electromagnetic waves are waves that correspond to photons. So you can also see that this says that EP is equal to h bar omega k as an equation between vectors. You see, the E is the first, and the P is the second equation. And this is actually a relativistic equation. It's a wonderful relativistic equation, because energy and momentum form what is called in relativity a four vector. It's the four vector. This is a little aside on relativity, EP. Four vector, the index mu runs from 0, 1, 2, 3. Just like the x mu's, which are t, and x, run from x0, which is t, x1, which is x, x2, which is y, 3. These are four vectors, and this is a four vector, this is a four vector, this all seemed quite pretty, and this was associated to photons. But then came de Broglie, and de Broglie had a very daring idea that even that though this was written for photons, it was true for particles as well, for any particle. De Broglie says, good for particles, all particles. And these particles are really waves. So what did he write? He wrote psi of x and t is equal to a wave associated to a matter particle, and it would be an e to the I kx minus omega t. That's a wave. And you know that this wave has momentum, P equal h bar k. If k is positive, look at this sign. If this sign is like that and k is positive, this is a wave that is moving to the right. So P in hk, if k is positive, P is positive, is moving to the right. This is a wave moving to the right, and has this momentum. So it should also have an energy. Compton said that this is relativistic because it all comes from photons. So if the momentum is given by that, and the energy must also be given by a similar relation. In fact, he mostly said, look, you must have the energy being equal to h bar omega. The momentum, therefore, would be equal to h bar k. And I will sometimes erase these things. So what happens with this thing? Well, momentum equal to hk, we've already understood this as momentum operator being h bar over I dvx. So this fact that these two must go together and be true for particles was de Broglie's insight and the connection to relativity. Now, here we have this. So now we just have to try to figure out what could we do for the energy. Could we have an energy operator? What would the energy operator have to do? Well, if the energy operator is supposed to give us h bar omega, the only thing it can be is that the energy is I h bar dvt. Why? Because you go again at the wave function. And you take IH bar ddt, and what do you get? IH bar ddt on the wave function, is equal to IH bar. You take the ddt, you get minus I omega times the whole wave function. So this is equal H bar omega times the wave function. Like that. So here it is. This is the operator that realizes the energy. Just like this is the operator that realizes the momentum. You can say these are the main relations that we have. So if you have this wave function, it corresponds to a particle with momentum hk and energy h omega. So now we write this. So for this side that we have here, h bar over I dx of psi of x and t is equal to the value of the momentum times psi of x and t. That is something we've seen. But then there's a second one. For this psi, we also have that I h bar ddt of psi of x and t is equal to the energy of that particle times x and t, because the energy of that particle is h bar omega. And look, this is familiar, and here the t plays no role, but here the t plays a role, and this is prescribing you how a wave function of energy E evolves in time. So you're almost there. You have something very deep in here. It's telling you if you know the wave function and it has energy E, this is how it looks later. You can take this derivative and solve this differential equation. Now, this differential equation is kind of trivial because E is a number here. But if you know that you have a particle with energy E, that's how it evolves in time. So came Schrodinger and looked at this equation, psi of x and t equal E psi of x and t. This is true for any particle that has energy E. How can I make out of this a full equation? Because maybe I don't know what is the energy E. The energy E might be anything in general. What can I do? Very simple. One single replacement on that equation. Done. It's over. That's the Schrodinger equation. It's the energy operator that we introduced before. Inspiration. Change E to E hat. This is the Schrodinger equation. Now, what has really happened here, this equation that was trivial for a wave function that represented a particle with energy E, if this is the energy operator, this is not so easy anymore. Because remember, the energy operator, for example, was p squared over 2m plus v of x. And this was minus h squared over 2m d second dx squared plus v of x acting on wave functions. So now you got a really interesting equation because you don't assume that the energy is a number because you don't know it. In general, if the particle is moving in a complicated potential, you don't know what are the possible energies. But this is symbolically what must be happening, because if this particle has a definite energy, then this energy operator gives you the energy acting on the function, and then you recover what you know is true for a particle of a given energy. So in general, the Schrodinger equation is a complicated equation. Let's write it now completely. So this is the Schrodinger equation. And if we write it completely, it will read I h bar d psi dt is equal to minus h bar squared over 2m d second dx squared of psi plus v of x times psi of x and t, psi of x and t. So it's an equation, a differential equation is first order in time and second order in space. So let me say three things about this equation and finish. First, it requires complex numbers. If psi would be real, everything on the right-hand side would be real, but with an I, it would spoil it. So complex numbers have to be there. Second, it's a linear equation. It satisfies superposition. So if one wave function satisfies the Schrodinger equation, the sum of wave functions, and another wave function does, the sum does. Third, it's deterministic. If you know psi at x and time equals 0, you can calculate psi at any later time because this is a first order differential equation in time. This equation will be the subject of all what we'll do in this course. So that's it for today. Thank you.
All right. So let's jump back here. So there was a lot of stuff covered here today. I think rather than try to recall everything from the lesson, I'm going to try to explain what the notes are because I think that's going to be a little tricky. There was a lot of math covered, and the math is what's important for this lecture particularly because this was a sort of mathematical class rather than a conceptual one like some of the other ones. So let's go back to, okay, here we are, lecture 5, beginning of the notes. So we sort of reviewed some things here, and then we introduced operators. So operators are things that take one object, turn it into another object. The analogy is with matrices. So matrices, I'll just move this over here. Actually, I should, this way. Matrices take vectors and turn them into other vectors. And so the operations we're going to be considering here are complex functions going to other functions. I mentioned sort of a programming analogy here, and then we just went through some examples of operators. And then in particular, we're looking at linear operators that respect this superposition relation. Basically, that you can, the operator of the sum of two functions is the same as the operator applied to one function times the operator applied to the other function. So you don't, you can kind of add them together. They don't have some sort of complex dynamical effect. A question I asked myself was, is convolution a linear operator? I'll save that one for later. I think I'm going to try to buzz ahead, but that was something that came up in my thoughts. Convolution is an operator where you take two functions and you multiply them, but it changes the direction of the time. So what else did we cover here? Eigenfunctions and eigenvectors. So eigen it means characteristic. So it is the characteristic function of an operator or the characteristic vector of a matrix transformation. And essentially it's the one that only changes to a factor of scale. So the exponentials are the eigenfunctions of the derivative operator because you take the derivative of e to the x and you get what? You get e to the x again. And so because there's a whole family of these complex exponentials, or includes sine waves, includes all these things. These are all eigenfunctions of derivatives. If you take, in general, we're talking about this, so the eigenfunction of the momentum operator, which is this thing, is going to be these complex exponentials. And then what did we do? We did a little bit of, so we figured out the energy operator. So the energy operator here was the second derivative of the position with this sort of, these constants on the side, plus this potential function. So the potential function is just simply because if we are not on a flat surface, if there's a height well or this kind of thing, then the energy is going to change because of potential energy. We just basically derived this from taking the momentum operator, getting the kinetic energy plus the potential energy, and we were able to get the exponential, and so we defined it this way. Then we looked at the observable. So the idea being, what's the importance of these operators? Well, the operators are important because the operators are the things that when you do the when you apply the operator to a particular wave function, what we actually observe is an eigenvalue corresponding to a particular eigenfunction. So that's why these things are relevant. So the momentum operator, what we observe when we look at it is this momentum eigenvalue. So one of the frequencies, let's say, of the function. If we do the position operator, we get one of the spots from the delta function. The energy value, we observe one of the energy levels that was implicit in the wave function. And so we're doing it this way. I'm not entirely sure why this particular sequence is correct for getting this. So this is something maybe to derive later. I'm not going to go through it right now to prove it to myself, but this, why it's complex conjugate first, then the operator, and then this, I might have to look at that again. And we talked about it, operators don't necessarily commute, so like the same thing with matrices, order is very important when you're doing it. And in particular, we defined a piece of notation, the commutation. So the commutation, if you take two operators, you just sort of say AB minus BA of those operators. And if they commute at 0, if they don't commute, it means that there is that they're not independent of each other. You can't measure, you can't do one without the other. So you can't measure one without without introducing sort of this uncertainty. You can't measure them both at the same time. That would be the right way of putting it. All right. So this is, again, this operation is that the operation is what we're measuring is these eigenvalues. There's a little side note here that they should be real, and that corresponds to a type of operator known as a Hermitian operator, which will be discussed later. And then the second thing is that once you measure the system and get this eigenvalue, it collapses into the eigenvector that corresponds with it. So when you measure position, you find it in one place and the system collapses. When you measure the potential, I imagine it collapses into that eigenfunction. All right, and then given the observable A hat and the eigenfunctions of this, essentially just the way we did with the Fourier transform, where we took a function and represented it as sine and cosine waves, what we're doing here is you can take any function and represent it as a superposition of those eigenfunctions. So you could take any given wave and build it out of sine waves. You could build it out of delta functions. You could build it out of energy states, which are going to be more complicated, I imagine, but visually speaking, but they're going to also be something you can build it out of. And then finally, the probability of observing any of the particular eigenvalues is going to be based on this equation here. So that he did sort of an example here for the for this, and then this sort of all of these ideas are coming together in the Schrodinger equation, which is basically the time evolution of the wave function. So far we've been taking psi of x, which is sort of a snapshot of this wave function, and now we want to introduce, well, it's changing over time, and the end result of that was this function right here, which is a second order differential equation, which is taking this evolution in time and this evolution in space plus this potential, and basically that it is going to, this is how it's going to evolve in time. Now, I think this is related to general wave-like properties that you have second derivative in x related to the first derivative in time is this sort of waves themselves, so that how they dissipate and flow and whatnot. But this is basically, if we have psi at any given time, knowing this, we can see how it will evolve in time. So how it will spread out and shape and vibrate and fluctuate and whatnot. So let's just take a really quick recap of what what we're kind of feeling, what I'm feeling good about, what I'm feeling like I maybe need to study a little bit more, or practice a little bit more. I'm going to avoid doing a lot of heavy stuff with the math right now because I think the problem sets are going to be the real test of that. I like to do problem sets first before I start playing around with the math too much. I have done a little bit of things, but I feel like it's going to be easy to go down some rabbit holes where I'm trying to derive things that I can't actually derive, or I'm going to be trying to prove things that, well, this is actually was just stated earlier. So I usually like to get my hands in some problem sets first. But we have about 25 minutes left before I'm going to take a break for lunch. So the question is whether I want to jump right into lecture 6 right now, or whether I want to take a break and do some kind of mini Feynman technique or something like that with this material. What do I think is the most confusing, or what is the most difficult about this material? I think most of this makes sense. I think the math is going to be, again, the thing that's a little bit challenging conceptually. I mostly understand it. There's a few details that I'm not entirely clear on, but they might get cleared up when I start actually doing it with the problem sets. So in particular, like this idea right here of why is it this particular order is not so clear right now to me. We kind of worked out the kinetic energy. We paused to do that. So I feel okay about that. I feel okay about eigenvectors and eigenfunctions, generally speaking. What else? I feel okay about how the Schrodinger equation was derived, so I feel fairly good about this. I'm just going to add a little note here because I think this is sort of important of what we're dealing with operators and these eigenfunctions, is that we have this psi function, which, as we know, like if we take the real part of it, can just kind of have any shape. So it could be anything, really. This could be this potential of this eigenfunction. And we can think of different ways of decomposing this function. So one would be to take it as all little delta operators. Another way would be to add in different phases and frequencies. And this one we could also imagine taking it at different energy states. Now, I don't know what the energy state eigenvectors or eigenfunctions are going to look like for this. But let's see if we can't get a little picture of that for the eigenfunction. So what does the energy operator look like? Let's go back to it. So the energy operator, where did we derive it? Here. Okay, so the energy operator is the second derivative of x plus this potential. So if we don't have a potential function here for this energy operator, then it is just this second derivative of x is forming this energy thing here. And this is otherwise just going to be a constant. So this is also going to be, I believe, this is also going to be waves as well. That this is going to be broken up of. But whereas these ones were the first derivative, if I'm not mistaken, of the psi function, this is the second derivative, the energy function. And so these are different ways of building it up. So I like to, when I do this, this is obviously the sort of mathematical component, but I like to give myself a clear analogy or a clear visualization that I can use as a reference point, so that whenever I'm getting confused again, I can use that as a landmark to go back to. So I'm gonna create a little analogy right here based on this. So one way of imagining this is, let's say we are building a house. So let's say we're building our house. So let's say psi is equal to this house that we're building, and we can imagine the different decompositions of this. So the different kind of, let's say, operators and eigenfunctions of this house building operation. So maybe one of them is going to be slices of the house. So one of them could be just sort of like, okay, this is the first foot of the house. This is the second foot of the house. The third foot of the house. All the way up to, you know, the roof and stuff. So we can imagine slices. So this could be like a slicing operator. And the eigen functions would be these slices. So these would be the eigen functions of these slices. And then, I mean, this is a complicated object, but we could imagine that the eigenvalues would be probably some kind of, you know, the amount of that is in those slices. And then let's take another example of maybe another operator we could do. Maybe it would be so we're doing slices. So one challenge with this analogy is that this eigenvalue, as I've stated it, is not necessarily enough to reconstruct the house identically. If I just take a slice and I say there's, you know, 50 feet of lumber, it doesn't necessarily know what pattern it forms. So that's going to be a downside of this analogy. And sometimes your analogies aren't going to be perfect, but as long as you are aware of those defects of the analogy, it can still be useful to have them. So maybe another decomposition could be, let's have like a weight operator. So it could be just sort of like how much each component, we just have it is broken into, you know, like 1 kilogram pieces. And then this could be sort of our eigenfunction. And then the eigenvalue would be maybe what these pieces contain. And then another example might be, what would be another possible operator we could apply to this house to decompose it into components. Maybe there's a, what would we do? Well, maybe we looked at slices this way, so we could also look at slices this way, right? If we're doing with this operator, we could look at slices of this way of the house. To these slices, and it could be the same thing. So this could be like a horizontal slicing operator, and this could be a vertical slicing operator. So the idea that I want to communicate, or I want to think about with this metaphor, is we're thinking about taking some complicated object and breaking them into components so that you can completely build them out of these smaller components that are themselves simpler and have a simple kind of pattern. So this one eigenfunction of the slicing operator is going to be these individual slices of the house, and that they're going to have a certain, you know, value that lets me reconstruct the original house, or its weight operator, or vertical slicing operator. And that basically we were decomposing the house into all of these pieces that we could build it out of again later. And the weakness of this analogy is that maybe we wouldn't be able to completely reconstruct the house if we cut it apart too much. So we just have to imagine that we can. And to understand what the eigenfunction is here, is that we have to understand that this eigenfunction corresponds to this operator if we do a slice. Well, if we had a house that was just a horizontal slice, for instance, it was just a flat piece, we would get one slice out of there, and all we would need is the eigenvalue to decide it. So in this case, the eigenfunction, or the what is sort of like an eigen that will just what will be a house that just has one eigenfunction would be just a slice. This would be just one chunk. This would just be a vertical slice. So these are different ways of going through it. So I'm going to keep this kind of analogy in my head. I mean, this is not a rigorous mathematical analogy, but I'm thinking about taking something complicated and decomposing it into chunks in a systematic way. So slicing, weighing, vertical slicing. Similarly, when I'm doing this thing, I can look at where it's located. I can look at its momentum. I can look at how much energy it has. And something that has a well-defined energy is going to be in a stable energy state, but that's also going to mean that it's not necessarily going to have a well-defined position. So, okay, so I feel pretty good about this. I mean, I think we're gonna have to go to problem sets to really get our hands on things. I think doing more Feynman techniques right now is probably not the best idea, just because I think I want to do the problem sets first, and I want to make some more progress. Now, I'm a little bit slower than I was hoping. It's day 1.5, and we've been through 5 of the lectures. So I think my goal would be to get through maybe, I'd like to hit 8 today. So I think I'm going to switch and go on to doing lecture number 6 right now, and do it for 15 minutes, break for lunch, and then come back at 2 p.m. So just some people ask some questions. So talking about, so one person said, I thought I did this course, the MIT challenge. No, I didn't. Someone's talking about mentioning this on your CV. I think you have to explain what you mean by doing it. So I wouldn't say that I got credit for these classes, but you could explain that, you've covered this material so that an employer might, be able to test you on it, or be able to say that you know these things. But definitely it's unethical to say that you've gotten credit for these. I make a big point of not saying that I have an MIT degree or anything like that, because I obviously don't. So I think it's important when you're talking about whether you've done these before is to explain what you've done. Now, I think that's a little hard on a CV or a resume, so I'm not sure whether I'd include these on the resume or the CV without some kind of preamble or some kind of explanation. But I mean, if I did a big project like the MIT challenge, I might explain why, even though I don't have a computer science degree from a university, I feel like I have quite a bit of computer science knowledge. So let's go on to lecture 6. Again, there's still some stuff that's a little rough around the edges, and I think we're going to be really tested on that when I get to the problem sets. But let's not waste too much more time. Let's just go straight into lecture 6. Try to get done up to 10 so we can start working on these problems hopefully tomorrow afternoon.
The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseware continue to offer high-quality educational resources for free. To make a donation or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.
Oh, this is still lecture 6. Hold on a sec.
So,
The following content is
Oh
provided
no,
under a
we
Creative
did
Commons
lecture
license.
6. So this
Your
is lecture.
support will help MIT OpenCourseware
Oh,
the following content is provided under a Creative Commons
I'm
license.
getting ahead of myself. We are doing lecture 6.
MIT OpenCourseware continue to offer high-quality educational resources for free. Or to view additional materials from hundreds of MIT courses, visit MIT OpenCourseware at ocw.mit.edu.
so finally, before I get started on the new stuff, questions from the previous lectures. No questions? Yeah, good. Excellent. Okay. Excellent. Those will be posted on the Stellar page later today. Okay. Yeah.
Okay, so we're associating operators with everything.
Yes. Okay, so let me rephrase the question. This is a very valuable question to talk through. So thanks for asking. So we previously observed that observables are associated with operators, and we'll review that in more detail in a second. And the statement was then made. So acting does that mean that acting on a wave function with an observable is like measuring or with an operator is like measuring the observable? And it's absolutely essential that you understand that acting on a wave function with an operator has nothing whatsoever to do with measuring that associated observable. Nothing. Okay, and we'll talk about the relationship and what those things mean. But here's a very tempting thing to think. I have a wave function. I want to know the momentum. I will thus operate with the momentum operator. Completely wrong. So just before even telling you what the right statement is, let me just get that out of your head. And then we'll talk through that in much more detail over the next lecture. Yeah. We're doing everything non-relativistically. Quantum mechanics for 804 is going to be a universe in which there is no relativity. If you ask me that more precisely in my office hours, I will tell you a relativistic story. But it doesn't violate anything relativistic at all. We'll talk about that just to get a little more detail. That will be a very important question that we'll deal with in the last 2 lectures of the course when we come back to Bell's inequality and look at them. Other questions? Okay, so let's get started. So just to review where we are. In quantum mechanics, according to 804, our first pass of the definition of quantum mechanics is that the configuration of any system, in particular, I'm going to think about a single point particle. The configuration of a particle is specified by giving a wave function, which is a function which is wave dependent on time, but a function of position. Observables, and this is a complete specification of the state of the system. If I know the wave function, I neither need nor have access to any further information about the system. All the information specifying the configuration of the system is completely contained in the wave function. Secondly, observables in quantum mechanics are associated with operators. Something you can build an experiment to observe or to measure is associated with an operator. And by an operator, I mean a rule or a map. Something that tells you, if you give me a function, I will give you a different function back. Okay? An operator is just a thing which eats a function and spits out another function. Now, operators, which I will denote with a hat, as long as I can remember to do so, operators come, and in particular, the kinds of operators we're going to care about, linear operators, which we talked about in detail last lecture. Linear operators come endowed with a natural set of special functions called eigenfunctions with the following property. Your operator, acting on its eigenfunction, gives you that same function back times a constant. So that's very special. Generically, an operator will take a function and give you some other random function that doesn't look at all like the original function. It's a very special thing to give you the same function back times a constant. Okay? So a useful thing to think about here is just in the case of vector spaces. So I'm going to consider the operation corresponding to rotation around the z-axis by a small angle. Okay? So under rotation around the z-axis by a small angle, I take an arbitrary vector to some other stupid vector, which vector is completely determined by the rule. I rotate by a small n, right? I take this vector and give me this one. I take that vector and give me this one. Everyone agree with that? What are the eigenvectors of the rotation by a small angle around the z-axis? Yeah, it's got to be a vector that doesn't change its direction, it just changes by magnitude. So there's 1, right? I rotate, and what's its eigenvalue? 1, because nothing changed, right? Now I'm consider the following operation. Rotate by a small angle and double its length. Okay, that's a different operator. I rotate by double length. I rotate and I double length. I rotate and I double length. Yeah, so what's the eigenvalue under that operator? 2, right, exactly. So these are very special set of functions. This is the same idea, but instead of having vectors, we have functions. Questions? I thought I saw a hand pop up. Yeah, okay, cool. Third, superposition. Given any two viable wave functions that could describe our system, could specify states or configurations of our system, an arbitrary superposition of them, an arbitrary linear sum, could also be a valid physical configuration. There is also a state corresponding to being in an arbitrary sum. For example, if we know that an electron could be black and it could be white, it could also be in an arbitrary superposition of being black and white. And that is a state in which the electron is not black, the electron is not white, it is in a superposition of the two. It does not have a definite color. And that is exactly the configuration we found inside our apparatus in the first lecture. Yeah. Excellent. So in general, the superposition, thank you, the next question. The question was, are these phi a's arbitrary functions or are they specific eigenfunctions of some operator? So the superposition principle actually says very generally. It says given any two viable wave functions, an arbitrary sum, an arbitrary linear combination is also a viable wave function. But here I want to mark something slightly different. This is why I chose notation. Given an operator A, it comes endowed with a special set of functions, its eigenfunctions. Right? We saw that last time. And I claim the following, beyond just the usual superposition principle, the set of eigenfunctions of operators corresponding to physical observables. So think your observable like momentum, that corresponds to an operator. Consider the eigenfunctions of momentum. Those, we know what those are, they're plane waves with definite wavelength, right? E to the ikx. Any function can be expressed as a superposition of those eigenfunctions of your physical observable. We'll go over this in more detail in a minute. But here I want to emphasize that the eigenfunctions have a special property that for observables, for operators corresponding to observables, the eigenfunctions form a basis. Any function can be expanded as some linear combination of these basis functions. The classic example being the Fourier expansion. Any function, any periodic function can be expanded as a sum of sines and cosines. And any function on the real line can be expanded as a sum of exponentials e to the ikx. This is the same statement. The eigenfunctions of momentum are what? E to the ikx. So this is the statement that an arbitrary function, when the observable is the momentum, this is the statement that an arbitrary function can be expanded as a superposition or a sum of exponentials. And that's the Fourier theorem. Cool? Was there a question? Okay, good. Yeah. Okay, other questions on these points? So these should not yet be trivial and obvious to you. If they are, then that's great. But if they're not, we're going to be working through examples for the next several lectures and problem sets. The point now is to give you a grounding on which to stand. Fourth postulate. What these expansion coefficients mean, right? And this is also an interpretation of the meaning of the wave function. What these expansion coefficients mean is that the probability that I measure the observable to be a particular eigenvalue is the norm squared of the expansion coefficient. Okay? So I tell you that any function can be expanded as a superposition of plane waves with definite momentum, with some coefficients, and those coefficients depend on which function I'm talking about. What these coefficients tell me is the probability that I will measure the momentum to be the associated value, the eigenvalue. Okay? Take that coefficient, take its norm squared, that gives me the probability. How do we compute these expansion coefficients? I think Martin didn't introduce you this notation, but he certainly told you this. So let me introduce you this notation, which I particularly like. We can extract the expansion coefficient if we know the wave function by taking this integral, taking the wave function, multiplying by the complex conjugate of the associated eigenfunction, doing the integral. And that notation is, and this round brackets with psi a and psi, is my notation for this integral. Okay, and again, we'll see this in more detail later on. And finally, we have collapse. The statement that if we go about measuring some observable A, then we will always observe precisely one of the eigenvalues of that operator. We will never measure anything else. If the eigenvalues are 1, 2, 3, 4, and 5, you will never measure a half, 13 halves. You will always measure an eigenvalue. And upon measuring that eigenvalue, you can be confident that that's the actual value of the system. I observe that it's a white electron, then it will remain white if I subsequently measure its color. What that's telling you is, it's no longer a superposition of white and black, but its wave function is that corresponding to a definite value of the observable. So somehow the process of measurement, and this is a self-serving statement, which will return. So the process of measuring the observable changes the wave function from our arbitrary superposition to a specific eigenfunction, one particular eigenfunction of the operator we're measuring. Yeah, and this is called the collapse of the wave function. It collapses from being a superposition over possible states to being an indefinite state upon measurement. And the definite state is that state corresponding to the value we observe or measure. Yeah.
So when the wave function collapses, does it instantaneously not form a function of time anymore? Because it originally been psi of xt.
Yeah, that's a really good question. So I wrote this only in terms of position, but I should more precisely write. So the question was, does this happen instantaneously? More precisely, does it cease to be a function of time? Thank you. It's a very good question. So no, it doesn't cease to be a function of time. It just says that psi at x, what you know upon doing this measurement is that psi as a function of x at the time which I'll call t star at which you've done the measurement is equal to this wave function. And so that leaves us with the following question, which is another way of asking the question you just asked. What happens next? How does the system evolve subsequently? And at the very end of the last lecture, we answered that. Or rather, Martin answered that. By introducing the Schrodinger equation. The Schrodinger equation, we don't derive, we just posit. Much like you can posit stuff equals ma. You can motivate it, but you can't derive it. It's just what we mean by the quantum mechanical model. And Schrodinger's equation says, given a wave function, I can determine the time derivative change of that wave function, and determine its time evolution. And its time derivative, its slope, its velocity, if you will, is 1 upon IH bar, the energy operator acting on that wave function. So suppose we measure that our observable capital A takes the value of little a, one of the eigenvalues of the associated operators. Suppose we measure that A equals little a at some particular moment t star. Then we know that the wave function is psi of x at that moment in time. We can then compute the time derivative of the wave function at that moment in time by acting on this wave function with the operator, E hat, the energy operator. And we can then integrate that differential equation forward in time and determine how the wave function evolves. The point of today's lecture is going to be to study how time evolution works in quantum mechanics and to look at some basic examples and basic strategies for solving the time evolution problem in quantum mechanics. One of the great surprises in quantum mechanics, hold on just one second. One of the real surprises in quantum mechanics is that time evolution is in a very specific sense trivial in quantum mechanics. It's preposterously simple. In particular, time evolution is governed by a linear equation. How many of you have studied a classical mechanical system where the time evolution is governed by a linear equation? Right, okay, all of you, the harmonic oscillator. But otherwise, not at all. Otherwise, the equations in classical mechanics are generically highly nonlinear. The time to change of position of a particle is the gradient of the force, and the force is generally some complicated function of position. You've got some capacitors over here, and some magnetic field. It's very nonlinear. Evolution in quantum mechanics is linear. This is going to be surprising. It's going to lead to some surprising simplifications, and we'll turn back to that. But I want to put that in your mind like a little hook. But that's something you should mark onto as different from classical mechanics. We'll come back. Yeah.
Continues the derivation not evolving.
That's an awesome question. The question is, look, imagine I observe. I'm going to paraphrase. Imagine I observe a particle and I observe that it's here. Okay. Subsequently, its wave function will evolve in some way. We'll actually study that later today. Its wave function will evolve in some way, and it'll change. It won't necessarily be definitely here anymore. But if I just keep measuring it over and over and over again, I just keep measuring it right there. It can't possibly evolve. And that's actually true. And it's called quantum Zeno problem. So it's the observation that if you continuously measure a thing, it can't possibly have its wave function evolve significantly. And not only is it a cute idea, but it's something people do in the laboratory. So Mark, you will. Okay. People do it in the laboratory. It's cool. Come ask me. I'll take about the experiments. Other questions very much. Yeah.
After you measure the Schrodinger equation, how is the evolution backwards in time?
Oh crap! Yes. Oh, that's such a good question. Okay, I hate when people ask that at this point because I have to then say more. That's a very good question. So the question goes like this. So this is going to be a punchline later on in the lecture, but you still only 100%. Awesome. So here's the deal. We have a rule for time evolution of a wave function, and it has some lovely properties. In particular, let me talk through this. In particular, this equation is linear. So what properties does it have? Let me just talk. So I'm going to come back to your question in just a second, but first I want to set it up so we have a little more meat to ask your question precisely. So let me note some properties of this equation, this time evolution equation. The first is that it's a linear equation. The derivative of a sum of function is the sum of the derivatives. The energy operator is a linear operator, meaning the energy operator acting on a sum of functions is the sum of the energy operator acting on each function. You guys studied linear operators on your problem set, right? So these are linear. What that tells you is if psi1 of x and t solves the Schrodinger equation, and psi2 of x and t, two different functions of position and time, both solve the Schrodinger equation, then any combination of them, alpha psi1 plus beta psi2, also solves, which I will call psi, and I'll make it a capital psi for fun, solves the Schrodinger equation. Automatic. Given two solutions of the Schrodinger equation, a superposition of them, an arbitrary superposition, also solves the Schrodinger equation. This is linearity. Cool? Next property. It's unitary. What I mean by unitary is this. It conserves probability. And you'll give a precise derivation of what I mean by unitary, and you'll demonstrate that in fact Schrodinger evolution is unitary on your next problem set. It's not on the current. But what I mean by unitary is that it conserves probability. What's that? It conserves probability. I.e., if there's an electron here, or if we have an object, a piece of chalk, which we're treating as quantum mechanical point particles, described by a wave function, the integral of the probability distribution over all places it can possibly be, it better be 1, because it better be somewhere, right? Probability 1. Then it better not change in time. If I solve the Schrodinger equation and evolve the system forward for half an hour, it had better not be the case that the total probability of finding the particle is 1/2. That means things disappear in the universe. And much as my socks would seem to be a counterexample of that, things don't disappear, right? It just doesn't happen. So quantum mechanics is quantum mechanics is unitary, and this is a demonstrably good description of the real world. It fits all the observations we've ever made. No one's ever discovered an experimental violation of unitarity of quantum mechanics. I will note that there is a theoretical violation of unitarity in quantum mechanics, which is dear to my heart. It's called the Hawking effect. And it's an observation that due to quantum mechanics, black holes in general relativity, places from which light cannot escape, evaporate.
So it's 11 now Pacific time, so I'm going to just take a pause. I'm going to be back right where we started. I'm going to be back at 2 p.m. and continuing lecture 6. My hope today is to try to get done, maybe, depending how fast I can go, maybe I can get done 8 lectures. That would put me in a good position for finishing up to lecture 10 by Wednesday morning. And then we have Wednesday afternoon, Thursday and Friday to get through the first 5 problem sets, potentially more if we have time. So I'm going to just take this moment right now to pause it. Thanks again for watching. I'll be back at 2 p.m.